January in Dallas Personal Robotics Group Builders Night Virtual. And we'll do the usual, go around the table. We have a handful of interesting topics tonight. Ross on the Readme platform and Git and some robot demo videos and who knows what else going on. Just a super brief housekeeping. I'll skip these parts on the left. We still don't have volunteers for the president, vice president, so there's still no meetings scheduled for those. Jack Jones, I've been working with him for a while, and he's got his presentation in, I'd say, a really, really good state. And so we're not going to put him off just because we don't have an election going on. So he's slated in for the 19th of February, the third Saturday that month, but he'll give his presentation on that. And then we have a handful of others in the wings of candidates for whoever wants to volunteer for the president role. We got, some things queued up that could make the job easier. Without further ado, we have, and in this order, just however it happened, we'll go around the table. We'll do Ted, and then Chris, and then me, Carl, and then Doug P., and then a free-for-all.
So I was just thinking about that, and I had a lot of trouble getting that right. But once I got it right, I think how I did it makes a certain amount of sense. So I thought I'd just present that. So the way I do it, I consider this, it's the same problem as driving a certain distance and stopping at that point. It's just you're turning a certain amount of degrees and stopping at that direction. So in my head, it's really the same problem, and I approach it the same way. So I'll present my screen here. Let's see, no, not that one. But yeah, and one thing, so to describe my robot, I've got some speed controllers that will, that use a PID loop internally, and so they can hold, you can tell them what speed in ticks per second to go, and then they'll go to that speed. And it's also nice, you can tell it a certain acceleration to use when doing that. So let's see.
Ted, is that a RoboClaw?
What's that? Yeah, RoboClaw.
RoboClaw.
Yep. All right, I am looking. So I want to find, oh, there's the window I want. Okay. So I will share that window. So this is kind of what my plan was. A certain distance or degrees of turn, and then also that some have a case where it's accelerating, but it's the distance is so short that it doesn't actually get up to full speed, and then it has to decelerate to the target. So the way to go, at least the way so here's the real case that I ended up doing is I accelerate up to full speed, and then I need to decelerate down, but I don't want to go down all the way to zero because sometimes it was overshooting or undershooting the target, just because in the real world, the acceleration isn't always perfect. And so I have this pad where it goes at some slow speed, slow enough that it can still move smoothly, but about as slow as it can go. And then when it gets to the target distance, then it decelerates. And really, that's more of a threshold. And that's kind of, I think, what we talked about a couple of weeks ago that David did, where there's a range of degrees or distance where you're trying to get to. And as long as it's in that range, then you consider
Circle.
it bound. Yeah, circle. If it's turning, then it's a range of angles, plus or minus 3 degrees or whatever. But yeah, for I found the best way to deal with this was just kind of do an internal simulation. So you're using the equations of motion and you're solving for a distance by taking the velocity you're currently going at minus, well, and you square that and then you subtract the slow velocity you want to get to, and then divide that by 2 times the deceleration. And that will give you a distance. So all you then have to do is look and see if that distance is, well, yeah, if it's less than the threshold, then you need to stop. If it's less than, or if your distance is less than that threshold, then you need to stop. Otherwise, if your distance is less than that D that you just computed, you need to decelerate to your slow speed. And if it's greater than that distance, then you're accelerating to your full speed. And so that seemed to work well for me. And I just made a short video of it, of my robot doing that. And I have it, in this case, spinning in place because it's a lot easier to test just spinning. And I set the acceleration fairly slowly. And let me see if I can find that video here. No, that is not it. There it is. All right. So I have it. Yeah, I have it accelerating fairly slowly, and it's doing several rotations. I think it's 4. So you can see it accelerate and then decelerate and then stop. So I will present that window and share that. And so here's my robot, and it'll start accelerating here and going up to speed fairly fast. And now it's decelerating and it stops. So all that seemed to work fairly well for me. That's all I have. If there's any questions.
I
Ted,
think
that's
that's
exactly
a gold star, right, guys? Gold star?
Now we have to think. Now, do you get a gold star if you just show a video?
No,
I think so. I think so.
Because
Yeah,
I could get a gold star every time. I got hundreds, thousands.
Well, no, but I'm just,
was
it's
a
got to be
video
new, Dave. It's got to be new.
Yeah, it
But-
was a video I just took.
Yeah.
Well, then we have to have a time frame as part of the calculation.
we
Let's
we
look
decided
at
2
cable.
weeks ago that a video, as long as it's new, would be sufficient evidence for a gold star. And if you think about it, that's
Maybe
necessary.
silver. Maybe
Because you've
silver.
got an outdoor robot.
Okay. It has to be in the last week. Otherwise, from the last meeting.
Fair enough. That's
Well, it is.
Fair
Would
enough.
be, right?
Ted,
Okay.
that's exactly how I do it on my robots. And your graphs basically could apply to my robots as well. And the problem you described when you're only moving a small distance, where you actually can't ever, at the given acceleration rate, you can't actually ever make it up to full speed. You start back down before you get up to full speed. That's fine. Those
Yeah.
small distances, it's really just going to bump over a little bit anyway. So
Yep.
you probably don't want to be going very fast to move a small distance. So that works fine.
Yeah.
So was your goal to do like
acceleration?
multiple 360s and end up, because you look like you ended up with the caster pointing pretty much in the same direction. Was that the goal to
Well,
zip
yeah.
around?
The goal was just to spin around to show you how it worked. It's easier just spinning around than trying to find a long space in my house to drive it and
Mhm.
without bumping into anything.
Oh yeah.
Ted, I'm
But
not sure if
did you
Oh, sorry.
try to get it so it ended up like multiple 360-degree revolutions because it ended up pretty much in the same point that it was
Right,
in
and,
when it
and that's
started.
what I set it to do. So it does about 3.5. Let's see, what is it? 3.5 ticks per degree encoder ticks. So I had it going 5,040, which if you do the math is 4 360-degree rotations.
Oh, okay. Yeah. That's what it looked like anyway. It ended up,
Yep.
stopping pretty much where it started out from. So.
Ted, there's another little tiny tweak you can do, which is that basically even when you decelerate, when you fall off the end of your ramp, your pad, even when you decelerate, the momentum of the robot takes a while to actually come to a stop. And you can actually measure that. That'll be, at the speed you're going, that'll be so many ticks, and then actually stop short of your goal that many ticks. And it'll exactly, you can actually tweak that.
Yeah, and I have actually done that. So
Okay.
it's about 5 encoder ticks.
To drift to a stop.
Yeah.
Yeah, exactly.
So Ted, your PID loop, what's the input and what's the output there? Is it are you controlling the velocity here?
So yeah, the PID loop's internal to my speed controller. It's taking care of that. The speed controller has the input from the wheel encoders, so it's doing it based on velocity, and it's also I give it an acceleration value. In this case, I think the acceleration was 100 ticks per second squared.
Mm-hmm. So you don't have a PID loop to set the acceleration or the velocity. You have a PID loop to control the voltage or the current that's going to the motors.
Yeah, sorry, I couldn't hear everything you were saying.
No, I was asking if you had the PID loop to control the voltage, the velocity, or is it the PID loop to get to control the motors, like adjust the voltage that goes into the motors to reach the desired velocity. I'm wondering where the PID loops are. Is it at the low level control, motor control only, or are you looking at acceleration and deceleration based on some kind of PID? With PID, the target, set target being the distance that you want to go and stop.
So, okay, so I think if I understand you, the PID loop is controlling the speed and acceleration of the motors.
Mm-hmm. Okay.
Yeah, that particular part you can do a PID for velocity or for position. So with the RoboClaws. So, but yeah, it auto tunes for you can have it auto tune for either. So that's kind of nice. It figures all that out for you.
Yeah,
this is all running down in the hardware controller. In other words, he doesn't have a PID loop that he's written.
Yeah, so Ted, you essentially input a speed and an acceleration, and I assume a deceleration. They don't have to be the same, right? You have
correct.
that goes into the RoboClaw. How does it handle the what do you call it? The shelf? No, you call it the pad. How does that RoboClaw handle the pad?
So there, so yeah, I give it the acceleration, deceleration value, which I use the same value for both.
Okay.
I could use different values. And the pad is just running at, I think I had it at 60 ticks per second. I just gave it that speed, and then I had it decelerate at that same range.
So you just when you reached the deacceleration, when you speed of the deacceleration, you knew when you got that reported from the RoboClaw, I guess, you just changed the reference value to get your pad for a short period of time, and then you decelerate it again.
Right. So I changed the speed to my slow speed, and then when I got to the distance where I was hitting my target, I had it decelerate to 0.
Got it. That's cool.
Yeah, I think for that one you can specify acceleration, deacceleration, velocity, and position all in one command if you want. They have a command that you can do that. So
Yeah, if you want.
yeah, lots of options.
Well, if you were using that to, control a CNC controller or plotter or axis, something like that, that would actually be exactly what you want.
Yeah.
Mm.
All right, I guess we're done here. Who's up next?
Pretty cool. Excellent.
Thanks,
Thank you, Ted. Gold star, man. Way to go.
Yeah, thanks.
Chris, I believe you're next in line. Then I'm on deck after that, and then Doug.
All right, so let me arrange a few things. So in terms of what I want to talk about, just two things. One is a quick recap of what I've had already in place on my Readme platform. Just basically documented a few things. I just want to walk those through because they kind of help for context. And then talk about what I've done recently. I had a little bit of time, and I've wanted to sort of actually accomplish something with that time. So I picked something relatively simple, and took a leaf out of Dave Anderson's book and implemented waypoint navigation. So I'm going to walk through what I've done there exactly. But again, first of all, before I get there, I just need to, set a little bit the context of what's going on my Readme platform. I think most of you have seen it. It's this guy right here. Wait, where am I? Okay, here. This guy right here, ultrasonics, infrared in the front, LiDAR on top.
We can hear 'em.
Differential drive.
Yeah, we can hear the LiDAR
Yeah, when you pointed it right at the mic.
or the sonar.
No, that was the
Ultrasonic.
sharp.
Sonar.
That was the sharp.
Hmm.
That was the sharp infrared. Is that what you mean?
Well, no,
we
we
can
can hear the sonar.
It sounded like a thumping noise.
Yeah,
I thought
There
it was
it is.
ultrasonic.
yeah.
You
Yeah.
might be right. I mean, I can hear it. I can definitely hear it. I didn't realize the microphone picks it up that much. Yeah. So exactly, I got two ultrasonics, the LiDAR, and my line sense on top, and B&O 085 on the bottom, and the QT Py on the bottom as well. But actually, I'm going to show that's the physical platform again. What is it? 8-inch diameter. Now let me just share my screen here. Entire screen. Which one? That one. The share. So this is a diagram I've shown before, but I'm just going to show it again for better context here. So again, I have a Readme control board that comes with the platform. I, maxing out kind of the I/O on that with the sharp infrared sensors and the ultrasonics. It's doing the, it's sending the PWM to the motors, and it's it's reading the quadrature encoders, and that's what it's sending back to the Raspberry Pi. And I'm moving from I2C to USB-based serial. I've mentioned that before. I haven't quite finished that switchover yet. Then I have a QT Py. That's another I/O slave, reading the line sensor array, and it's doing the I2C interface with the B&O, 85 here in the bottom. Then you see the LiDAR and my game controller there for interactive control. So again, all of that, I've shown that before. Most of you have seen it. Nothing new here. But so this is what the hardware looks like in terms of the software environment. What I have is I have a combination of it's all Python, and then I have a combination of software that I use outside of RAWs, and then software that I use together with RAWs, and I've structured it in such a way that, as you'll see in the next slide, making use of this in the RAWs context is just kind of another layer of software on top of this. So this is kind of just showing a couple of basic Python modules that I've created for some very simple use case of interactive control with obstacle avoidance. I might have demonstrated that at one point. Again, I'm driving with my game controller there, but it's not letting me crash into something. If there's nothing in front of me, it'll just go. If there's something in front or wherever, right, it'll steer away. So that's using the IR, and it's using the ultrasonics. It wasn't using the LiDAR. So far, it's not using the LiDAR. But this is all done without any use of RAWs. I'm pulling in the heading, I'm pulling in the joystick data. And then I have this big, giant Python main application that's doing most of the work that needs to be a bit refactored. There's too much going on inside this one module here. And some of it is separated out, like sort of the basic odometry calculations, the standard sort of odometry math, is separate, but there's more that ought to be separated. So the point is really, so this is kind of, because sometimes I like to work outside of RAWs, right? Maybe just to test things if I want to make sure my B&O 85 works properly. I have this weird offset that I need to bake into the final output, right? All of that is happening inside what I labeled the Qt Py driver, right? So there's certain things that I can just test like that without, firing up the full RAWs machinery, okay? Just sometimes, simpler that way. And, but most of the time, I want to do something, in RAWs. And so now, basically, then what I did is I've created, on top of most of these drivers, if you want to call it that way, I've created another layer of software that really does nothing else than just take care of the interfacing with the RAWs world, right? I mean, again, the data that comes out of the Qt Py, my lane sensor, and my IMU heading, that is the data. It comes out. How it gets, distributed to other pieces of software, that's really what this other layer does that sits on top of this. And it really doesn't do much than interface with this driver and then send the data out on RAW. So I have this kind of pattern in place, for most of my the things I'm doing. Again, I haven't done anything on the LiDAR side that comes for free. Like I said, on the left side here, there's still this one big blob that needs a bit of splitting out into separate modules. That's not quite following that pattern yet, but that's on my to-do list because I'm lumping kind of the closing the motor speed control loop together with the RAWs interfacing into one big application. Again, it gets a bit messy there. I need to clean that up a bit, but that's kind of the pattern I've been following, and I find it helpful that way, so I can switch back and forth between doing something super simple without RAWs, or if I have enough brain cycles left in the day, do something more sophisticated, with RAWs. It really depends on how much time I have and how much patience I have. So that's, again, this is not new content. This has been there. I've just kind of taken a bit of time to actually document it so I can explain to people what that looks like. Now, right, so just what does all this mean in the RAWs context, right? It's all these additional boxes there with the dashed line around it. Yeah, they just basically publish all this various information, and they subscribe to it. You think of the RAWs publish, subscribe, nothing more than just a bunch of global variables that you can read and write. One other thing that's shown here that I've mentioned in the past.
Oh, Chris, we lost you.
Oh no, network freeze. How cold is it in Connecticut? Even the internet's frozen.
Oh dear.
Oh no.
Yep.
Oh,
Chris?
no.
When this happened to me a month or so ago, I didn't know. And I just went ahead and I went ahead and gave my 20-minute presentation.
You might want to Carl type something.
Yeah.
Yeah, that's well. You can all type something, but let's see.
Or we all could. Yes, really.
Chris,
But
you're
it-
frozen.
Chris, come back.
Yeah. Chris, breathe. You look like you're not breathing. You're frozen.
No, let's see. Do I have his cell phone number?
Or the other option is
Just
knock
fix
him
the
off,
broken.
and then maybe he'll discover it and come
Looks
back.
like he left.
I
think
bet
he's
he'll be
solid.
back. My goodness, I have a dozen Chris's in my phone, and none of them are the one we need right now.
I suspect he saw the note, and hopefully he'll reconnect when he can.
Or we all froze on him.
Let's see. He made a sudden acceleration, and his time is just the other way around. Okay.
So are you guys seeing any freezing weather like last year?
Not yet.
It was in the 60s and 70s the last couple of days.
In other words, we're not to February quite yet.
Yeah, but we did have some 20-degree nights, 20 degrees Fahrenheit. So
True.
I think here it's minus 18 Fahrenheit. Minus 27, 28 Celsius right now.
Yowza.
I had to bring all my tropical plants into the garage.
I left mine in the snow.
I'm sending him an email.
Yeah, but who would look at their email if they think they're presenting?
Some
Yeah.
people have notifications, and maybe I'm on the respond immediately list. I don't know. I doubt it. But
And depending upon if it goes to his phone, because sometimes you can forward those things to phones.
But I don't see his. Surely he's left the meeting.
I think he's
Right,
left the meeting, I
so-
suspect. Yeah.
Yeah.
So
there's a question of how long we stall.
Because nobody else wants to go.
Well, do we really want to get started on another? Well, let me ask the question then. So, who wants to get on deck? So, I would go next, then Doug P. Who would go on deck after that? Anyone to queue up? Paul? Good. Anyone after Paul?
Well, I know that Chris had mentioned that he
I
thought,
actually have two things, and so one is real short. One's a robot demo shooting for a gold star, so I can use that to fill time while we wait for Chris to rejoin, and then after Chris finishes his talk, and when we get around to my turn, I've got
Okay.
something that is longer that people may be more interested in, or may be interested in.
Okay. Well, Paul, maybe you want to just jump in with the fast one then, and then if we still have time, I can do a fast one. And
Okay, so
faster
if you pin me, I'm going to use my camera to just demo the robot. And let's see. Are you all seeing Mobot there?
Indeed.
yes,
yes,
Okay, so I've made good progress with Mobot. And yeah, I've read the safety instructions. And so what this does is I've just plugged in the ESP32, and it's going to put the robot into bit test mode here shortly, which is done now. And then it'll turn on the flashing light, and then it'll give a motion command, and then
Oh, your carpet.
it'll turn off the flashing light, and then turn back on again and go backwards again. So, and then I'm going to unplug the ESP32 so it doesn't keep on moving backwards and forwards continually. But that's my demo.
Woohoo!
David is fast on the gold star, so you got one right away there, Paul.
Yeah.
Paul, I have a simple question.
What's that?
Which is the front end of that robot?
The rounded end is the front end. That's the mowing business. The wheels are at the back.
Okay. That's all.
Paul, did you manage to implement your velocity calculations using your period between your encoder ticks?
I did, Pat, and it actually worked as far as I can tell. But I didn't post it because I didn't feel like I'd done enough testing. But yes, I did measure the because I felt to really say, yeah, this works, I should put it in a closed loop with a PID controller and all that. But just measuring from the point of view of manually spinning the wheels, because I didn't have autonomous control of the wheels at the time that I coded up that odometry speed and distance calculator. So just from the point of viewing of spinning the wheels and observing that indeed I got counts that reflected what looked like a reasonable speed and reasonable distance movement, it looked like that mechanism worked.
Excellent.
That would be something that would be fun to see, Paul, when you get it where you feel you can present it. That would be really nice.
Yeah, I mean, it really was pretty much what I thought it would be, Doug, in terms of looking at the reading the timestamp when the interrupt comes in, sticking it in a queue from ISR down to base level, and then computing the number of milliseconds between that and the last tick with an upper limit, upper bound, at which time I declared the speed to be 0, but kept a track of the distance.
So you're not really, oh, wait, let me think. Okay, well, I say you're not really counting a clock pulse per se, except abstracted to a time.
Each interrupt tick, each interrupt, which happens every encoder tick,
Yeah,
results in reading the current millisecond timer
right,
and sticking that value in a queue down to the base level.
right.
And then the base level counts up how many time measurements it got from each wheel, and that represents the distance it traveled. And currently it takes the last time delta between the last two ticks and calls that the speed. If there were 2 ticks in the last time delta, if there weren't 2 ticks, then it says the speed was 0.
Gotcha.
Paul, thank you. Admirable job of ad hoc filling. If there's no other questions for Paul, then
Back to
we'll
Chris.
return to Chris. I think, Chris, you were...
Yeah, I'm back on, and I hope that's gonna stay that way. I'm just wondering if I need to turn off incoming video, just so I don't know what's going on with my internet. All right, sorry about that. So let me just pick right up from where we left it. Screen 1, share. Okay, so what I was saying here is, right, so this just really shows how I have taken just the non-RAWS code, layered some RAWS interfacing Python on top of it, and now, you know, all that information that gets produced by each of those nodes becomes available. That's just what RAWS does. No, including for visualization purposes, and I haven't shown that here, but that's of course one of the motivators sometimes for me, at least, to use RAWS, because you can visualize it very very nicely. So this again, this is as of months ago. This is nothing new here. So now, what I managed to do recently is two things. One is I've taken because sometimes I want to do something simple, right, and not in the full LiDAR scan data, whether it's in the form of a point cloud or just a standard LiDAR scan. It's just maybe too complicated to work with. Maybe for some simple obstacle avoidance, what I really want is just a bunch of, reasonably precise distance sensors. So I've created a module here that takes in the LiDAR scan, okay? And again, in ROS, it's straightforward. You just subscribe to it and voila, you have the information. And I take that in and I turn it into 12 virtual distance sensors. Each of them has a field of view basically of 30 degrees, right? So 360-degree coverage, almost like, think of it like I have now, sharp distance sensor coverage, all the way around my platform. Again, this is a very straightforward thing that you can do in RAWs. You take in this information and then you publish some new information, hoping that someone picks it up and does something with it. I'm not currently using that. Again, that would come in handy for some new obstacle avoidance logic, perhaps, that I might work on. So that's the plan for that. Now, to make that useful for visualization, I also had to update the JSON file that tells RAWs the position of each individual sensor, right? So that's, again, something I've mentioned in the past and maybe briefly shown. There is a description of the robot, in a JSON type format that tells RAWs the exact location of each sensor, or really the pose of each sensor, right? Where it is relative to the center of the robot and which direction it's pointing, right? My LiDAR happens to be dead center, right? That's straightforward. But some of these other sensors, they're somewhat off axis and they're pointing in different directions. So I've updated this so that, the nodes, any logic or the visualization, tool, if it wants to display all this information, it knows actually, where these 12 virtual distance sensors are pointed at, right? Because otherwise, all you'd have is, 12 numbers corresponding to those 12 sensors. And, you wouldn't know which ones, well, you would know which ones which. They obviously are numbered in a certain way, and you could hard code, which one corresponds to which angle and so on. But this, RAWs has its own elegant way of saying this sensor points in that direction, and and has this kind of field of view. So that's also part of this.
Chris,
Again, go ahead.
Just a question, that those 30-degree arcs, do you average together all of the measurements within that arc?
So good question. So I'm kind of been playing with both options. One is averaging, and the other, just I take the smallest reading and I use that as the reading. I haven't sort of used this enough to figure out what's best. I might also try something where I throw out some outliers, because if I pick up the smallest reading, there's a good chance there's at least one reading in there that's just some weird reflection, right? Where I'm picking up something that looks like it's close by, but it's not. It does happen, right? So I haven't experimented with this enough to know what gives me the best and most usable data. Okay, but right now I'm thinking I pick the smallest one. That way I'm it's kind of the safest thing to do, right? From obstacle avoidance point of view. Okay.
That sounds like a cool application for a tiny ML training, in a way. Might take some effort to do it, right? But you could train a neural net to take in that stuff, whether it's distance, and then you could have the neural net consider both spatially, right? However many sensors are in that cone, and then over time, and
Yeah, but you'd need to know, wouldn't you need to know the ground truth, right? Wouldn't you need to tell it, okay, in this situation, this would have been the best thing to do, and this is kind of what I
Yeah.
consider the good reading, right? So unless you tell it that, right, it's
Yeah.
not really.
I don't know
gonna
an easy
read.
way to train it, but it seemed like it'd be great if somebody could train it.
Yeah, because Chris, if I'm not mistaken, your 30-degree arc has 30 points in it. So there's very easy
More or
for
less,
you
yeah.
to have an edge. Otherwise, let's say you were cutting the edge of a box. So on one side, it would be where the distance of the box is. And on the other side, it would be wherever your wall is because you don't have an obstacle.
But then
so
again,
I think your selection of the nearest point is definitely the safest way to go. Do you see what I'm saying? Otherwise, if you had an obstacle here and you hit here, it goes way out. Here it goes way out. Here it goes way out. Here it hits the box. Hits the box. Hits the box. And I mean, because you're really looking at a 30 points, right? Or are you throwing points away?
No, I'm looking at all the valid points, and it's actually, it varies how many valid points I get, right? And it's I get more than one reading per degree because this version of the LiDAR, takes a lot more samples per second than the cheaper version of it. So I get a lot. I get usually on the order of, let's say, 400 to 500 valid readings per rotation.
Right. Okay. So
yeah. So it's somewhere, let's just say 40 valid readings per 30-degree cone, and if all of them are valid, they're usually not. And those that are valid, I picked the smallest one because that's, again, it seems to be the safe thing to do.
That makes sense.
There'll be situations where that's conservative, but again, I'll have to see how that plays out once I actually make use of it for obstacle avoidance. So right now that's there. I'm not using it yet, but that's kind of next step. But so the other thing I did that I'm sort of more proud of because it's kind of cool and at the same time is simple. But I haven't really done it before in my own way. I've used RAWs in the past. The RAWs navigation stack, certainly can do a lot of cool things, and I've demonstrated some of those. But again, that's where once you get into the RAWs navigation stack, you just got to dedicate some time to it and brain power because it gets overwhelming real quick. All this other stuff here that I'm doing with RAWs, again, it's fairly straightforward. It's really not that hard, but it's those. Again, the RAWs navigation stack, there's just so much going on there that it's hard to get your arms around it. And so, David presented this sort of waypoint navigation, and I went back to look at the presentation. I said to myself, hey, this actually is very straightforward in a way, right? And he laid it all out, with code in the PDF there that's on the DPRG website. So I literally went there, looked at the code, and literally, converted it into Python code in just almost one-to-one, and put a RAWs wrapper around it. I've used the same pattern that I've talked about earlier. I have a module here that's just implementing the core of the waypoint navigation, those same functions that David has listed there in his presentation. Literally, there's the same functions with some tweaks that I can go into, and then it's a matter of feeding this with the information and taking the output out, and the output that comes out here is the same output that in my interactive control, my joystick kind of produces. So right now, in the absence of any fancy multiplexing or arbitration, I can do one or the other, right? I can do interactive control, right, which would publish, right? If you've seen on the previous slide here, interactive control produces kind of this velocity command, or I can do waypoint navigation, which also produces a velocity command. And the input to this waypoint navigation is really primarily the current pose of the robot, which in Raw's world, is usually published on this topic called ODOM. That's the convention. And of course, a destination, which I'm not doing anything fancy right now with feeding it the destination. It's just kind of a command line parameter, very straightforward. I'll show that in a second. But it's doing what it's supposed to do. And let me just switch here for a second to another screen. Like I said, I've literally taken from this presentation, I've literally looked at these implementations here and converted them into Python code. Now, I did bang my head against the wall a little bit, David, in some cases here. And part of it was because in Raw's world, the way the angles work was a little different. So in your case, where's your starting point here? When you're pointing north, there's one diagram here that kind of shows what's considered, a theta of 0, and it's different, and when you turn left, I think in your case, theta increments, or whichever way it is, it's the opposite for Raw's, right? The way Raw's does the coordinate system. So that caused a little bit of confusion. I had to sort through that in my head, and trigonometry late at night is a pain. And so that was the only tricky part, really, getting it right with the what's considered a positive direction turn versus what's considered a negative direction turn, etc. And the implications of that, had to be accounted for. The other thing, David, just FYI, that I ended up having to do in my code, because it took me a while to get this working. You have x comma y here, atan2 x comma y. When I looked on the internet, sort of how this atan2 function is usually used, I saw it was producing the output that I thought I wanted when I do atan2 y comma x. Again, I didn't really get too deep into the trigonometry. I just saw a diagram online that showed atan2 y comma x, and it showed what angle it gives me, and it all made sense to me. So I used y comma x, not x comma y.
Y comma x is the standard. If you look up, and if you remember in my talk, I even addressed that. I said if you look up in your 8th grade trigonometry book, it'll tell you y over x, and what that does is gives you the angle relative to the x-axis. But what I wanted was the angle relative to the y-axis, which is.
Oh, okay.
So I'm sorry if that wasn't clear, but I have to say, bravo.
Well, I should have rewatched the YouTube video, which I didn't. Right, I went straight to the slide and copy and pasted the code, and lo and behold, it didn't work exactly right. So that's fine. I figured it out. And so you'll see it in a second, but I've literally copy and pasted your snippets of code into Python, and magically it worked. I mean, I was amazed. It took a little bit of tuning of my admittedly very primitive water control, because it kind of wasn't responsive enough. But okay, why is this not connecting now? Come on. All right. So I don't know how small or big that is on your end, but I made
Perfect
this
size.
Yeah, great. So again, David will recognize this, because again, this is copy and paste from his code, with some tweaks. Target acquired. He had a function there that just tells us if we're inside this error circle, and and if we're starting to get worse, then we better call it quits. Now again, it actually took me a little bit to get that to work, because for some odd reason, most of the time, my distance and last distance kind of was the same. I didn't quite catch sort of the case where I'm inside the error circle, and then it's starting to get worse. I'm starting to get out of it again. So I had to add this plus epsilon here in order for this to work. And I haven't done the root cause on it. I don't know why, but that's otherwise I never, I didn't catch the case of, oh, I'm in the error circle and now I'm starting to drive out of it again. So that was a little odd. Target vector, that's one of the core functions there. That's calculating the actual bearing and distance relative, to the target. The other thing, David, I did in my implementation, I passed more information around as parameters. I was trying to not use sort of globals, but that's just cosmetic. Also, I did, and again, I didn't listen to your talk again, so I know you're doing a certain special thing with angles. You're just letting it accumulate, right? But I'm used to sort of normalizing and keeping all my bearings to within plus and minus 2 pi. So I'm doing that here because I found that
David
necessary.
does that.
I think that does the same thing, Chris.
Yeah.
It's just I'm doing it with a what looks kind of like a floating point modular function.
Okay.
But it basically does the same thing. If you overflow pi, you're subtracting underflow.
Okay. And then the main function is I give it the current position. Well, okay, 3 values, current pose, and where am I going? And it calls these other functions. Now here's where then I tweaked it a bit more relative to what you had in your slides, David. And I don't know if on your real robots you're doing something more sophisticated, but what you had is basically, well, if the bearing within the dead zone, don't bother steering, right? Otherwise, if we're off one way, just steer hard left. If we're off to the other side, steer hard right, right? It's kind of the logic you had shown in your presentation. And I found that to just, I just found that to oscillate around too much. So what I'm doing instead is something it's like, has some proportional aspect to it. If my bearing is off by more than 80 degrees, well, then I'm gonna steer as hard as I'm gonna steer, okay? And I'm also slowing down my linear speed, right? Because what I found the robot was doing, as its steering is also driving forward too fast, right? And then so it's making very wide turns. And if I know I'm way off in bearing, I'm basically not allowing it to travel forward as fast. And so it's almost like it's rotating in place until we get, close to the desired bearing, right? So it's something like that. You'll see it in the second, in the demo. But, once our bearing is a little bit more manageable, like less than 80 degrees, then how hard I steer then becomes a function of how far off the bearing is. So I found that to give me on my platform a smoother response compared to the logic that you had outlined in your presentation, David.
Chris, I can make a comment on that. Earlier on in that presentation, I talked about how I use a slew rate limiter on all the commands. And what that slew rate limiter does is basically the longer the command persists, the more sharply you turn.
Okay. Yeah, I have that also baked into my motor control, but I guess somehow the dynamics of my setup were a little different, where I found that this logic was, again, I ended up with too many oscillations, so I built a little bit of a proportional aspect into here.
I have a couple occasions tried to set up so that the steering was proportional to the error and angle toward the target. That is to say, the larger the error, the more sharply you turn. But I found it squirrely. I found the response squirrely. So I'm glad you've been able to make it work. I'll have to go back and look at what you've done here.
Well, again, it's kind of the interaction between this and the lower level speed control, right? I mean, there's the dynamics there. And again, my lower level speed control right now is a bit primitive. and so I found this to work. Yeah, and then this is okay. This is straight out of your book here. You just once we're close enough, we're kind of starting to ramp down in speed. And yeah, and that's basically it. And so again, this is the non-RAWs. There's nothing in here that has to do with the RAWs, right? Like I said earlier, this is the pattern I'm using. I'm putting the core logic into something like this. I can run this file as is. Some of the other ones, I have loops in here that run some test code. In this case, I had just a couple test cases here, that spit out the calculated distance and bearing and other things. So I know that I'm getting all my trigonometry right. But that's the usual pattern. So this is just by itself doesn't do much. It's really meant for combination of testing, in which case this runs, or to be included, into some other piece of, Python code. Another piece of code that does the RAWs, RAWsification of it, if you may. And that's what this is, and what really there's more there than there's sort of a couple things there that obviously we'll look for, and to those of you who are not familiar with RAWs, but at the end of the day, it's actually relatively straightforward. I take in the pose of the robot, right? That's the input I need for my waypoint navigation, and it comes in a certain way in RAWs, and I remember it here in some global variables, but it comes in every time I get one of those messages that get published by my actual odometry node, and it comes in here. But then there's a main loop, a very straightforward main loop. Again, the data comes in on its own. I don't have to do something about it. The data comes in the background asynchronously, and I just run through this loop at 20 hertz. That seems sufficient. I run through. I just feed the robot's current pose, which again comes in the background. I don't have to worry about that. It just comes in. It's just there. I feed that into the the waypoint navigation function, and out comes some status about how far we are off, etc. And out comes, of course, the main thing, which is okay, how fast should I go and how hard should I steer, and that I take that, right, those outputs, put them into another sort of raw data structure that's commonly used to tell some other node how to control the robot's velocity, and I publish it, right? And someone else will pick it up and do the low-level motor control with it. And so, so I just run through this loop until target is acquired, and then we're done. So that's basically, as simple as that. So what that looks like, let me show it. In the interest of time, I'm going to show the video because I don't have to fumble with the robot. And apparently you still get a gold star if you show a video that was recorded recently. So let me, if I can't find my OBS. Okay, so let me just switch here. So what I'm doing here in the recorded video, it's running all these RAWs nodes that I've talked about, and then the waypoint navigation, I'm just running it in the loop here. I'm telling it, go to position 0, 0, then go to X half a meter out, Y 0, and then the next corner of the square, next corner of the square, etc. It's just traversing a square that's basically half a meter on each side. And I don't have a huge amount of space, and so that's why it's such a small square that I'm making it traverse. And what that looks like, so what that looks like, I need to go back to my camera, and I need to, because the way I'm doing it, I'm going to switch here. So this is what it looks like. No, wait. No, this one. This is the recording. So So that's my 0, 0. And then again, so it's going through the loop now, going basically half a meter every time. And, you can see that it's almost like it's turning in place, not quite, right? So initially, if you remember what I said about when my desired heading is kind of way off, I'm kind of almost making the robot turn in place, because if I didn't do that, I found it was making pretty wide turns, right? And I don't have a ton of room here for wide turns. So this will happily do its thing. Over time, the odometry will drift. I am using the IMU for heading, but nonetheless, it's not terribly well calibrated. But you can see it's staying on the four corners reasonably well. But it will eventually just kind of drift off to one side or the other. My error circle is very small, so if it appears off, it's not because I have a big error circle. I've made that as small as I can get it without kind of oscillating, but it's really just the odometry is not all that great, and so eventually it just kind of drifts apart, away from these waypoints that are really reflected in these corners of the square.
Hey, Chris.
Yes.
What would be cool is to take your speed that you went to 0.1 and change it for, say, 0.2, 0.3, 0.4, and just watch the different, and you'll see that curve become bigger and bigger and bigger at each corner. It would be fun to see that.
Chris, that's excellent. Especially the fact that the way you're navigating, you can real clearly see it correct.
Yeah.
So that is to say, it rotates, it overshoots, it pulls back in. So it's clearly not just trying to drive in straight lines. And you totally deserve 2 gold stars.
1 gold star.
Oh, 1 gold star.
One gold star. That's fine. Yeah,
3 gold stars tonight. This is I think a record. So,
I do have a couple of comments, but I'll wait until you're done.
yeah,
well, I'm basically done. So I think I showed I showed my diagrams, I showed the code, I showed the video. So that's it's really open for questions at this point.
Well, this is just a minor point. On the robots that I've implemented, the robot knows when it's arrived at a waypoint, and you can do things when you arrive at a waypoint. For example, you might want to try to contact an orange cone, or you might want to try to grab a can and take it somewhere, or you might want to put a can down that you're carrying. So there's basically a hook that allows you to do things. One of the things you can do when you get to the waypoint, if it's enabled, is you can rotate to point to the next waypoint. And I found that that's a whole lot more efficient way to go from waypoint to waypoint. So there's just a function that you hand it the number of degrees. It's very much like what Ted was describing earlier. And it rotates through that number of degrees. That way, you're not saying rotate 90 degrees because you might not have arrived directly square on the waypoint. So you're saying rotate until you point to the next waypoint. And that's basically when I eventually got rid of steering proportionally. That's the thing that I put in. I can also enable and disable that. If you disable it, it does drive sort of big, funny oblong things. And if you're fast enough, it can even draw what looks like a circle. I mean, it'll just hit the corners.
Sorry about that, guys. My setup's shaky today.
Do I need to repeat all that?
Just the last 15 seconds. 15 seconds.
Ray says no.
So yeah, I heard you say, well, before, you can do something when you've reached the target, such as turn towards the next waypoint.
Yeah.
That's the last thing I heard.
Yeah. So basically, when it grabs the next waypoint off the list, when you've arrived at the waypoint, one of the things it does is check to see if there is another waypoint on the list. And if it is, and if a flag is set, it can rotate toward that before it releases control and goes on back to the navigation. You can also turn that off. And my last comment was that if you run fast enough around a square, it'll almost run in a circle with that turned off. It'll just hit the corner points. but you don't really want to rotate 90 degrees at the corner because you might not have entered at 90 degrees. You want to rotate toward the next waypoint.
Right, right. Yeah, I don't have a concept yet of a waypoint list. That's right now. It's really primitive. I mean, it's like a one shot. I invoke my waypoint navigation module, with the target that I'm trying to reach, and when it reaches, well, it's done. It quits. So it's very, I don't have the list yet or anything more sophisticated. That'll be next.
Well, I know everybody has their own habits. One of the habits I have is I tend to leave test code like that in the robot, so that anytime down the road, I had to replace a wheel or there's a broken gear that I had to go in, and that I can go back and run those original tests. The only difference is I've got, I think, 6 built-in patterns to go out and come back, to drive a square, to drive a triangle, to drive a figure 8. And those are all normalized values. And then I have scalars I can stick in. So if I want to go forward 8 feet, I say, do list number 1 with a multiplier of 8.
Okay.
Anyway, I just find it really useful to leave that stuff in. Later on, when you add things, it's always good to have those tests there.
Any other questions?
Excellent. And I must say, I think you're the only human on the planet that's ever implemented that.
Oh, I don't know. I think I have too. But Chris, I wanted to, another thing, I wanted to show you how I handled that same problem that you're doing there at the end of how to get the sharp corner. Now, I'm not saying it's the answer. I'm just saying it's how I do it. So let me present this real quick. Okay. Oh, wait a minute. Oh, here it is. Okay. All right. So somewhere in my loop, I come in here and I have I actually have a rotation flag, and I run a function called determine rotation in place. And if that, I just set if it's on, I set the forward speed to 0. That would be your 0.1. And then if I don't, then I just let it be the motor speed. If I go to the definition here, what I'm doing is I'm actually looking at it. If the heading arrow is greater than 15 degrees, then I put that flag on. And then if it's on, and then if it's less than 2, then it'll turn it off. So you can play with those when it kicks in and when it kicks out. And that's something that I just wanted to show you how I approach that same problem.
Okay, cool.
Okay.
Cool. Way to go.
Yep.
Thank you, Chris. All right.
Yeah, right.
Okay, if nothing else for Chris, then I'm going to jump in. I got a shorter thing
Carl,
and a longer thing. Yes.
I was furiously trying to put together a Pi camera so I can actually demonstrate some progress. So actually, I have maybe 5 minutes I can show at some point.
Aha. Okay. Do you need to do it sooner? Or do you okay do it a little later or in loop or?
Up to you.
Okay, I'll just put you in line with the queue. So we've got, I have a shorter one and then a Git thing, which is a little longer. Then Doug has a shorter one. Paul has a longer one, and then you have something. So it could be a good long night if we do everything in that order.
Okay.
All right. So what I have is, if you would like to pin the one of me that's talking right now, I'm going to show progress. And Raj, you may recognize this robot. Wait a minute. I'm going to show it after I select the right camera from this tool. Take me a second.
Is it duct tape unveiling robot?
Duct tape on baling wire. Yeah. So you may have noticed, Raj, some pushes to the commit on those repos we share, but here we go. So finally, it wasn't so good the last couple weeks, but now I've made a bunch of changes, and it's basically working about as well as I care to make it work at this point. And it just keeps going back and forth, more or less. Okay. So this is like I put in a Slack. This is using a heading PID loop based on a BNO 055 in fusion mode, and then the cone detection, which is pretty much the same Raj as what you had. I did some tweaks to it, and then so if it sees the cone, it feeds that straight in in a proportional loop. But if it doesn't see the cone, then it follows the IMU with a PID. So it's kind of like one or the other. And it's an open loop on the velocity to the motor. So it's there's no encoders or anything. I just set it to a certain speed, and that's why it's faster downhill and slower uphill. And
what's it doing there, Carl?
When it's wobbling?
No, it approaches the cone, but it hits some.
Oh yeah. Well, so there's like two stages of the cone detection.
Okay.
The one is to detect things with the right color and the right like aspect ratio. So I look for something that's at least like 1.5 times taller than it is wide.
Mm-hmm.
And then the second level is that if it sees if it sees the width of that bounding box to be a certain number of pixels or greater, then it declares a touch. So it doesn't have a touch sensor or anything. It just goes by the width of the detected cone.
So that's by design.
Yeah,
All right.
I mean, this is duct tape and baling wire. So
yeah. Before you were having an issue that when you where when you backed up and you went forward again, it kind of went off into the woods. What did you fix there?
Yeah, well, I believe it's very similar to essentially what David did or described, where you set the heading to the waypoint you're aiming for, not a fixed number of degrees from.
Oh, okay. All right. Yeah, okay. So you used heading there. Okay, I got it.
Yeah. So it was, so finally when I put that change in, it worked pretty well.
Yeah, it looks like real good. It looks like Mr. Carl gets a gold star for me.
Woohoo.
Yeah.
4 gold stars. Gosh, guys.
It's a big night for gold stars.
Oh, the big guy. I might run out of internet bits. I might have to use zeros. Oh, well.
Could be. So anyhow, that felt good. I mean, it still has a bunch of issues, but the next one for me is going to be doing something with a much better quality in implementation. So
that looks really good to me. Great.
Well, thank you.
I mean,
okay. And now for this next thing, if you guys are good for it, this could take, I think, 30, 40 minutes unless we talk a lot. And this is last week or so, there was discussion and interest on Git. So I've pulled together a kind of a demo that I'm willing to walk through. And okay, so speak now or forever hold your peace, hearing nothing. All right, so what we're going to do is we're going to build a Git repository from scratch, and we're going to play with GitHub, and we're going to look at how it looks in Visual Studio Code. So what you're seeing here is my PC, and on the C drive, we're just going to watch, how we start from scratch, starting on a PC, and then turn it into a Git repo. And I have my notes on the side here. So first, what we're going to do is, I have this file folder called Git Fun. And what I'm going to do in here is open VS Code on that folder. And, I have all the right stuff in here for these things to work. So we're not going to talk about setting it up. But I'll just make a file called main.txt, except I spelled it wrong, did I? Yep. So we'll fix that to be, all right. So, and then what we'll do is we'll put some text in there. I'm just going to copy paste from the other screen. All right, so you'll notice as soon as I did that, you see how this up here, is this big enough? I can make it bigger.
It's big enough.
So what you'll notice is that when the file is empty, there's nothing. But as soon as I make a change, like pasting something, it turns, the X turns to that dot, which means I have unsaved things. So I save that, and now it's saved. And all right. So then we'll notice that there's a folder view for this Explorer, and then there's the source control. If we go to source control, there's nothing in there. So I'm going to show you. So let's do it the manual way. So what you can do is open a terminal window in VS Code and run git init. So it initialized this as a Git repository. And what that did over here is in the file system, you'll see it made this hidden folder. And inside of that's a whole bunch of stuff you don't want to touch. So we're not going to do anything except look at it that exists. And now you'll see that in here under the source view, we have this blue one, which shows that we've made some changes. And but at the moment, I think it says, yeah, U for it's an untracked file. So Git knows that this file's in the file system, but it's not tracking it just yet. So what we're going to do is make our first commit. So I got some commit text here. I'll come over and under the source control thing, I do a checkbox, enter a commit message, copy paste, hit enter. Whoops. And why is this not working quite? Oh, I know why. Those of you who know Git will have noticed I skipped a step. First, I have to say I want to track this file. So I hit the plus sign, and now you'll see that that went from a change in the file system to a staged change, which means that it's been added and it's now being tracked by the Git tool. I can undo that if I want and pull it out. So now it's in changes, and if I add it plus, it's now staged again. And if you watch on the side here, nothing changes in the background when I do that. But what's happening is that the Git is making reference changes inside the database in this hidden folder. Okay, so we got this now file is now staged. So we're going to make a commit. So we're going to copy the text. We'll hit that up here, enter a message, and we've now made a commit. And you'll notice again, nothing changed in the file system, but we know that by doing that, stuff changed in the Git repo. So I use a plugin for VS Code called Git History. So we'll open that up, and what it shows now is we've got a commit made by so-and-so user, date and time. This is a unique hash. So Git computes it goes through all the files in the working directory, and it computes a hash. So you get a unique ID for that configuration of whatever files are in the structure, right? And we have the master branch. This is a branch at the moment. So now, yeah. And now we're going to add some more code so you can toggle between files this way. So we're going to add some more content to that file. So I'll just copy paste this period there. We'll add that. You'll see the circle thing came. So we'll save this file. And now if we come back over here, you see that under the, it still lists the file. That didn't change over here. But under source control, it now lists that file as having changed. And if we click on it here, you'll see that it shows, okay, so this was what it was before. Now we've added a period, so you can see it's kind of highlighted over here. And it's got this new line. So it's got the changes color-coded in red and green. So what we'll do is we'll make another commit. So we'll stage those changes. They're now staged. Then we'll make another commit. So I copy the text message, I paste it in, hit go. So now we have another commit. Come back over to this tool and you do a refresh. And now we have the first commit and then the second commit. So the first commit, it lists versus previous. There's nothing to show because it was a new file. If we click on this, it says compare to previous. Oh, here's all that's changed. So, and you see here, these are the hashes, BO4 blah blah to 335 blah blah. And if you look in here, there's the BO4 to the 335. So it gives you really good traceability from one thing to the next, right? So any questions so far? Okay, so the next thing we're going to do, because there was a question last week about, well, what happens if, don't you have to create the repo?
Carl, question.
Yes, sir.
How did you get the Git history to show up again? Did you just write it up in the command line?
No, so there's a lot of ways to do it. And if you click on this, it shows the extensions. And I have installed in VS Code Git History and Git Lens. So,
and so you just clicked on it there.
Well,
and the extension?
No, Control Shift P brings up the list of tools. So I can search here for like Arduino and find all of the commands relative to the Arduino extension, or I can search for Git. I said I can search for Git. Control Shift P, Git. So these are all the different text-driven commands that start with Git or include Git.
Okay, so it's the old Control Shift P command.
The old Control Shift P trick.
Oh, okay.
Yeah, it's very handy. It's a good way to leverage extensions in VS Code. Okay, so let's make a repository in GitHub. So we're going to make a repository, and we're going to call it DPRG Git Fun demo, and we're going to make it public, and we're not going to do anything else. Well, I'm going to copy it to the working notes. Okay, we're going to create that repository. All right. So at this point now, we've made a repository in GitHub, but it's empty, right? So I'm going to copy and you can get at it a lot of different ways. So I'm just going to copy the URL and I'll put it into chat. Where did the chat window go? For anybody that wants to, I wouldn't say screw with it, but follow along. We'll see you, Raj. I think he took off. Okay, so the other thing we're going to do with that URL is we're going to come back to our VS Code on local, and we're going to open this. And now what we're going to do is we're going to do so I'm going to teach you a new command. If we do git remote -v for verbose, we see that there's nothing listed. So now if we do a git remote add origin, okay, so what we're going to do is we're going to add a new remote to this local repository on my hard drive. We're going to call it origin, and we're going to say that remote is located at this URL. Make sense? And now if we do a git remote verbose, now we see that we have a remote called origin, and it's pointed to that URL. Okay, and you'll see that in the background, nothing's changed in the file system, but we know that if we look in Control Shift P, Git History, we'll see that it doesn't show that yet. But now what we can do is we can take this little cloud thing and we can say, let's publish, this is the master branch that we're still on. And there's only one branch, master. So let's publish that. So what it's doing is pull request. No, we're not going to create a pull request. Okay, we'll do a pull request just because I can't remember what I intended to do. So we're going to merge changes from into. Okay. So now if we do a refresh here, we see that we have this green master, which is the master branch on the local PC. And then we have origin/master, which means that there is this same commit is available on GitHub on the master branch. Okay. So now if we come back to that, if we go up here, there it is. And here's main.txt. So there's that same file we created on local, and we just pushed it straight up to GitHub. And there's only one branch. Okay, so that takes us now down to step 10. Okay, so now we're going to go back to local and start having a lot more fun. So what we're going to do is we're going to make a new branch on local. Okay, we're going to do create a new branch. And because we haven't selected any point to take it from, we're going to create a branch from the head, which is master, which is this commit right here, the newest one. We're going to call the branch pretend new feature branch. Okay, and you'll see it down here. It's changed.
Carl, I didn't see that. Where did you invoke create new branch from?
Well,
From which view?
in VS Code, if you go to this point down here, and click on it with your left mouse or whatever you have set up, your primary.
Okay, it's on the branch symbol. Okay.
Yep. It lists the available branches. So you can see now we have on local pretend new feature branch. On the local we have master, and on GitHub origin we have master, and we see that those two are at the same commit, and pretend new feature branch is also at the same commit. So and if we refresh, you'll see that all three of these branches are now pointing to the same commit, the same file set. Make sense? Okay, so now that we're operating on this new pretend feature branch, we see the spelling error, so we're going to fix that. Okay, so that's good. Change is there, so we'll save it. And you notice that it cropped up as one change, that file changed. And we're going to add a new file. So let's go add a new file, foobar.txt. All right, so here we're on foobar, and we'll give it some mumbo jumbo inside of it. Oops. And we'll save that sucker. And now you look over here into the change list, there's two changes because these two files. This one is untracked file because we haven't added it to the repo yet. We haven't told Git that we want to follow it. And then this one has been modified, main.txt. And we're going to do one other thing. Okay, so I have, just give me a moment to find it. Here we go. Okay. So if you've been watching in the background here, you'll see our local file system has foobar and main. And I'm going to take one more thing, and this is, come on, what am I doing? Second. We're going to take a file that has my notes that I've been following, and we're just going to paste it in. So you'll see that I just pasted it in the file system. But guess what happens? Git running here in VS Code knows that it just appeared out of nowhere because it's watching that whole folder. So it knows this is a new file. Get it? So what I can do is, let me open this to follow along. Okay, so now, let's see, we're on step 13. So now what we're going to do is we're going to add all these things to a new commit. So we'll just take, if we make this wide enough, well, we'll just do them one at a time. So we'll go, no, we got to go in here. We go, yeah, so we have all these changes, 3 changes, and you can see I can add foobar. So now foobar is staged. So if we would do a commit, only the changes in foobar would be saved, not the other changes. Or you can just say add all the changes. So now it's taken all those changes that it was aware of and it's added them. So as soon as we make a commit, it's going to be added to the repo. All right, with me. So we're
Didn't
gonna.
didn't you just start an edit on that last file that you didn't finish?
I saved it when you weren't looking.
Oh, okay.
Yeah. So like if you see up here, right, there's no solid dots. As if I would do spaces, then there's the dots.
Well, I thought I saw you on the desktop. I thought I saw you do a edit in Notepad.
Oh, yeah, I haven't changed anything over there yet. That's on my side. Too many windows. Okay, so, and then we're gonna add, just a second, 3 added. All right, so, all right, so let's make a new commit, right? So we know the routine, there's the check mark, you got the source control selected, so you do it here, you do the paste routine, add extra space. So now we have a new commit. Okay, and now if we go back to our Git history and do a refresh, and you'll see something funny, right? Well, where'd it go? Where'd the new change? But then if you look closely, you'll see that Git, in this Git history, in this view, is only showing changes in the master branch. This would show all the changes in the new feature branch, but I like to show the all branches. So now you can see that on local, master and origin pointing to this configuration, whereas the new branch is pointing to this configuration. Okay, so we have basically 2 branches and a copy of the one branch up on GitHub. Now watch what happens in the background, and then I'll pause for a minute. So you notice, remember down in VS Code, we have pretend new feature branch selected, and you can see the 3 files because we just added some and made some changes. So what happens if we,
Hold on, you did a commit, but you didn't do a publish. Can you explain the difference?
well, yeah, so
Commit only committed to local, and publish will publish to the origin?
it'll, yeah, wherever you have, whichever remote you're publishing to. So right now we only have one remote, and this thing knows, I mean, since it's only one remote, it knows that I want to push it to the one remote.
Well, what I'm saying is you've got a button there that says publish branch.
Where does that?
Your upper left says publish branch.
Yeah. So
when you did a commit, what's the difference between a commit and a publish?
Well, the commit makes new references in the local thing that you're working on.
Right.
So the commit says, I want you to make a new hash, so what it'll literally do is it'll make a copy of the current snapshot of files, or those changes in those files. It'll bury a copy of that here in this hidden folder and all the references to keep it straight.
Right. No, that's not what I was getting at. Is I thought you might have been glossing over that. I think I understand, but I think you need to make it important to those not familiar with source control, the difference between a commit and a publish. The commit's local.
It's only local. It's only local.
And when you do the publish, then it will match your local. It will basically match your local repository with the remote repository.
It'll push when you publish. I'll show you that in a minute. See, I never used this button, so I didn't even notice it. I usually just go down here.
Oh, okay. So I tripped you up. Go ahead.
That's all right. No, it's a good question. And that's what I was saying. There's so many different ways to do things. You just have to find one that works for you. And
one more fundamental question. So there's so many Git related extensions, and I have a couple of them installed in VS Code, but you seem to have a different one installed. So, okay, is it the Git history one that you were just using? Because I didn't get the Git history command that you were referring to. So that must be the extension you are using.
Yeah.
In this walkthrough.
I just like Git history as the extension because I like the way that it draws history in here, and
Okay.
I've gotten used to it. I know that like Steve, our Microsoft Steve, who Chris you haven't interacted with much because he's not been online that much. but as a full-time professional guy at Microsoft, he really likes Git Lens, from what I remember.
Yeah, I have that one installed.
Yeah, I was noticing that, Chris. It was showing you what line, on what line of code, who last changed it, and all that kind of stuff. I thought it was kind of cool.
Yeah, there's some neat, yeah, like look at that. I did it 4 minutes ago, and it's got a lot of nice features. And I got to tell you, when I look at the code that my developers in India are doing, I can hover over and it's like, oh, you did that 4 years ago. It's like, it's really helpful what it does. So again, so I was going to show you. So now, just if we watch down here, so we're on the pretend new feature branch, and the file set looks like this. But if we remember, right, if we click on this new pretend new feature branch, we added these new files, right? So if we go to previous, that's a new file. That was a new file, and this one just had a couple. The main just had a couple changes. So so what happens now? Let me clear that out. If we select down here and we check out, so you can check out a branch or you can create a new branch. So let's check out master. Did you see the files change in the background? Watch this. Let's check out pretend new feature branch. And when I do that, watch over here in the file system. Okay. So as I'm toggling between here, between VS Code and Git, what it's doing is it's putting the file system at the newest commit in this branch. So the newest commit in this branch for the master only has that one file, but the newest commit in pretend new feature branch has these other files too. See how that goes?
So is it updating that one folder with all that stuff?
Yeah.
What happens if you made changes before you did that?
Well, let's just do that. So let's come in here and say foobar, because Doug asked. We'll save it. All right. So now you see how it flagged that there's a change now. So this is a really helpful thing to watch over here. And if we flag over it, and if we select that and click foobar, what changed? And it says, oh, well, we've added this new line. So now you want to know what happens if we go and we select a different branch. So remember, this is a change in the file system, but it's not staged, right? It's a tracked file. It's been modified, but it's not staged. So let's go change to the master. And it says your local changes will be overwritten by whatever you check out.
That's what I wanted.
Yep. And it has, I wasn't going to cover stashing, but it's got a clever little way where if you wanted to like temporarily do something, you could take these. If you didn't want to commit them, you could stash them off to the side and bring them back later, but I wasn't going to go there. So normally I would say this. I like to think simple. So you'll notice that it has this button up here where I can, if I hover over it, discard changes. Do you want to discard the changes? And the changes are what's listed. There. Now it's back to normal. And if the way it was before, and if I switch to master, makes sense?
So if you're sitting there hovering over the text of your programmers in India, you can just undo everything they did?
Well, I mean, it's probably not quite that simple, but yeah, I mean, yeah, I don't know all the Git tricks to do that, but there are definitely ways that you can go cherry pick this commit or that commit and pull it out or push it in, and there's all kinds of crazy.
And cherry pick is the key phrase there. That's a real command inside of Git to go pull that. And as far as wiping things out, though, they should be pushing things into a branch to then eventually do a pull request in the master. So if you don't like what they did in their pull request, you wipe it out or don't pull it in. So
Exactly.
you're not wiping it out. You're actually not wiping it out. You're just going to say revert this file back to whatever it is in master, and then do your PR. And now you've effectively wiped out their changes without you having to go through and wipe out all the stuff and undo things and all that kind of junk. Yeah.
I do that in my own code. Let's
But-
just go back to the last one that worked.
That's the perfect reason for you to use Git, David.
Exactly like this.
Because I want to do this dumb thing that I have no idea if it's going to work or not, and it's going to take a lot of work to get there, and I'm not going to remember everything I did. Okay, Git checkout -b my stupid branch, and now everything you do is going to be the thing that Carl's been showing you. And if you decide you don't like it, Git branch -d, and the branch goes away.
Yeah.
So that's one of my questions: is when do you make the decision to create a branch and work on something rather than just make another commit on the main origin branch?
There's a whole bunch of theories of that. I don't mean to be stepping on Carl here, but that's a religious thing you just brought up, Pat.
That's the PID loop of Git.
Yeah, that's the PID. Like, when do you create a branch? And if you listen to the people that I work with every day, you create a branch at a drop of a hat to do weird things. And then the idea of the branch is, I'm going to do this. I have this concept. I'm going to make this concept work, and hopefully that concept is very, very small, so I can do it in just a few things. And then once I know that part does what I wanted to do, I'll create a PR, so I do the commits up to it. And now master has my stuff, and then I'll create another branch off of that to do the next thing that I want to do. I myself find it hard to do that. And so what I will do is I'll have a general concept or a task. The task is make the light blink in our case. And everything it takes for me to make the light blink, I create a branch right then. And everything I do to make the light blink, once it's blinking, I'm happy no matter what I got to do and where I got to do it. And that's the commits. That's another religious thing. By the way, is how often do you push that commit? I think early and often. So that when I have to back something out, I'm just backing out one or two commits, not a whole bunch of stuff. So, and then once you get that to a happy place, wherever that place is, or a very sad place in Dave's case, but a happy place, you're like, yeah, I like that. Okay, then that right there becomes a branch you want to do a pull request on and save for prosperity, that sort of thing. Does that make sense?
I think there are two different contexts, and that point is not being addressed by the answers that are being given to the question of when should I create a branch. The two contexts are you're collaborating with others or you're working on your own. When you're collaborating with others, you would always create a branch.
I agree with you, Paul. I agree.
Any new work, because you don't want to screw up what other people are working on. Main is considered golden. And so then when you're finished and you're ready to release your work to the rest of the group, you merge your branch into main. The other context, which I think many of the people on this call are looking at and asking about and thinking about, is where you're really using Git as a sort of storage for intermediate work products that you're not sure if you're going to keep or not. And there, I think the answer is a little more complicated. There, it's not as important to make branches. You may still want to for your crazy experiment like Harold was talking about. But in the course of ordinary development, where I've reached this certain point and I'm happy with it, I want to commit it, then I'm going to work on some more, you really don't need to make branches. You can just commit straight on a list of commits up main. So then the answer is really dependent on which of those two contexts you're in.
I would offer a third way to view it, Paul, and that is that at some point in mind, we have these robots that tend to evolve quite a lot over time, and the idea we start off with doesn't always become the thing that we implement in the end. So the way I like to think of it is that there's, at any given time, I like to think of one branch, whatever I call it, that's going to be the one that's the latest stable kind of branch. And then when I want to go and try other things, then I'll pick a stable point. It's a known, really well-known quantity. Like this was the point in time of the latest contest, right? So I'll say I'll make a branch from the latest contest and start adding a new IMU or a LiDAR or something. And then at some point that'll keep carrying on and on and on. And I'll say, oh no, I want to take a detour and go add some neopixels. So either inline or separate. And then at some point I say, well, now it was stable back then and I just kept building on it. Okay, which one is going to be my latest and greatest stable? I can keep working on the current one, or I can just merge it all back and have, so it's just.
So you end up with a bunch of branches at times that never get merged back with the main.
Sure. I don't delete things. They're just references to me. I never delete them, and it's interesting to me when these get really big to see all of the different branches and the way that it meandered around. So I just leave it in place because it doesn't hurt anything. Doesn't take any space.
Your new branch, when you're adding a feature, like you say, your neopixels, that could become your new main branch.
Yeah, and that's how it is. Like in the duct tape and baling wire one, I forget what I called it, but I haven't merged it back into the main for a long time, just because it was stable enough as it was.
So Carl and Paul and Harold. So for us, which our team consists of us, one person, usually. So you're saying that if you were going to introduce a new feature, or if you're going to refactor some code, those would be where you would do a branch, right?
Yeah.
Maybe. I would.
Yeah.
And unless the new feature, like I for a while I had a heading PID loop branch, and whenever I wanted to work on the heading PID loop, I would update that branch to the latest stable, and then I would do the latest and greatest improvement to the heading PID loop, and then I would merge it back to main. And I found the advantage to that is that then, like, using this filter tool, because when you have commits as often as you should, like Harold says, you're going to have page after page of commits. What you can do then is say, okay, show me all of the heading PID loop commits, so you can see those changes that kind of move that feature along forward. So it gets to be an interesting way to help filter and sort through all the mess that is software development.
Well, that one there has answered a lot of questions for me about branching without having to merge back into the main branch. So I'm going to take it off in a different direction, but I don't want to lose my base code from the original.
Right.
Absolutely.
Yeah. And it's what's nice is that it's all stacked in time, right? And it shows if you make the changes properly using Git, then they're all referenced to each other, and you can see a good progression.
And also, it's out on GitHub, so that if your code gets lost because you dropped a hard drive or something like that, you can get it back.
Yeah.
Mm-hmm.
Yeah, that's why I didn't build my own Git server.
Okay, let me ask you this, Carl. Let's say you're working from two machines.
Yeah.
How do you keep, so is it better to
Doug, that's a fantastic segue. So how about if I show you the next part of the demo?
Okay, go ahead.
So I think the question you're getting at is what happens if two different places or two different people or same person on two different machines are mucking with the same repository? What happens then?
Yeah.
Okay.
They do that because I have it on my laptop and I have it on VNC on my robot.
Exactly. We all do it.
Yeah.
Now you can create conflicts, and I'm not going to go through that. I'm going to go through the case here where you kind of consciously coordinated it, at least in your brain. There are ways to manage it if you change the same thing in two places, but that's like cherry picking, but it gets to be messy. So I was going to save that for later time. But for now, what I wanted you to just keep in your mind that we have now the master branch on local that just has this main file here, right? We have the pretend new feature branch on local that has these three things, but it hasn't been published yet. Okay. And then on Git, so if we refresh this page on GitHub, I mean, we only have one branch. It doesn't know about the other branch yet. Okay. So what I wanted to do up here was, let's say we're going to make a change to the same repo. Let's add a README. Okay. So I'll click the button to add a README, and just a second.
Add a what?
A README file, readme.txt.
.md, not read. It's markdown.
Oh, readme.md. Sorry, readme.md. Right, you got it. So we're doing that in GitHub, and I'll just put that text in here, and then so we're creating the new file via GitHub. So we'll commit it. All right. So now we have the case where the master branch on GitHub has two files, right? But the master branch on local has just the one file. So now what happens, and we got master checked out. So now you see, if you hover over down here, you got this synchronized changes thing. So let's click that button. And this actually...
Oh, I lost your audio. Is that just me?
That's just it.
Yeah, I can hear him.
Just you.
I lost everybody's audio.
Oh boy.
Great.
Okay, I'm going to keep pressing on. So now we have everything out of whack, right? So we have a new file in GitHub. And so we're going to take the master branch on local. That's checked out at the moment. And we're going to hit synchronized changes. And this says it will push and pull commits to GitHub, which is the origin master branch. So it does some thinking. And now, voila, we have the README file down here, showed up in the file system, right? We can even open it in VS Code. And if you have the preview available, you can see what it would look like in markup view.
Markdown.
Markdown, markup, mark sideways. And then if we refresh Git History, now it's starting to look interesting, right? So now we see the nice sequence in time. And we see that from the same point in time on here, we added some files and made some changes. And on this one, from this commit, we added this new file, right? So now we have master branch here in GitHub, and we have pretend new feature branch. And since we've done the synchronized, so we pushed and pulled. So we took the changes, pulled them down from GitHub, and we pushed them up from local. So now if we refresh this thing, we see that we have, prove me wrong. No, we just have the one branch because we still haven't pushed this branch back up yet. Pretend new feature branch. So, all right. So, and then if you notice that if we check out the pretend new feature branch, it doesn't have the readme.markdown yet. So, and if we check out main, and we don't have the foobar, so I got this to be a complicated thing. So, so the question now is, how might we patch these together, right? Let's say we want to take the feature branch and put it back into the master.
Well, Carl, how do you? Looks like the synchronized didn't work because you don't have the branch on your GitHub repository.
Oh no, the synchronize. Remember, I had master selected when I hit the synchronize.
Right.
Well, so what it did was it synchronized the master branch with the remote. It didn't synchronize all branches. So what you're asking is, if we check out the pretend feature branch, and now let's get that thing pushed up to origin master. Okay. So we
So you
synchronize
have, so each branch has to be synchronized. Okay.
separately. Yep.
Yeah.
So now
I mean, if you're using a command line, you can do it in one command line to synchronize all your local stuff and delete all your local stuff and that kind of junk. If that's what you want to go do, but that's a couple extra features.
Yeah.
like I say, there are a million ways to do it.
There's
I'm
a million
just
ways to
showing
do
you
it.
one.
There is.
Just showing you
Can
one.
you,
So,
can you show us the GitHub? Yeah.
yeah.
so
So
that we
now
can
if we
see.
look at GitHub, and what should we expect to see, right? Because if we look at this view, we see that the pretend branch on local should match GitHub and master should match, but they're just out of whack a little bit because they have changes that aren't synchronized, they aren't pulled together yet. So now we see two branches, right? And we can toggle. So the same commit, we can the same repo, we can have different views. This is on the GitHub view. There's the 3 files on new feature branch. Here are the 2 files on master. And you can look at you can list the branches. You can have any number of different branches.
It calls the other stuff.
So, so what I'm going to suggest now is that step 20 in this thing is that let's say we're happy with pretend new feature branch and we want to merge that into master. So all the changes that are in feature branch, we're going to put back in our mainline code. So I like to do it from GitHub. There's a lot of ways to do it, but what we'll do is I've got this branch selected and we'll say make a new pull request. And we're gonna try and pull the changes from feature branch into master. This green check able to merge automatically is good. If it's not like this, it means that you have conflicts. So you change the same thing in both places, it gets sloppy. But we were clean, so we're gonna make a pull request. All right. So now we've made a pull request and it hasn't changed anything. And you can have multiple pull requests open. So you can have a bunch of different things that you want to merge. It'll keep them all straight. So now if you select this pull request, then we'll merge it. Since it has no conflicts, it can be done automatically. So we'll confirm the merge. And it's been merged successfully. All right. So now, if we
Can
come
you
back,
unmerge?
say what?
Can you unmerge?
Nope. This is like the blockchain, baby. Once you've got it written in the blockchain, well, okay.
What you can do,
yeah.
What you can do is now when you've done that merge, you've moved the head of where your master was up to a new head that includes the changes of the other of the thing you just did. This head still here exists.
By the way, these are heads. These
they're all heads. Yeah.
These things right here are heads.
So and we refer to a lot of time these heads are referred to as a SHA, SHA. If you look on there, you'll see the SHA thing comes up. It's just a bunch of gobbledygook numbers. Carl has pointed out, right? So that SHA still exists in the world. It is not going away, even though you just merged and now this is your new main or your new master. If for some reason this is all going to crap and you want to go back to this, it's a fairly, you got to do the dance. And what you have to do is you'll have to, on your local branch, on your local machine, wherever you're doing this dance is, you're going to want to reset your current source location, source SHA to the SHA you care about. And once you have that, that's what you want. You've effectively reverted all the changes in that merge. Now to put that back in the master, you have to do the evil thing that happens all the time, but we call it evil because it is. What you'll need to do is you'll take this and force push it up to your GitHub repository, and now then you've effectively reverted that change. Did I say enough words to confuse enough people?
So basically, that's an undo command that you have to do manually.
That is an undo command, and it's made difficult like that because you shouldn't be doing that a bunch, and people do that all the time, depending upon the circumstances.
So what happens to all of the commits that were done after that point that you went and
They pretty much they have their own head and their own thing over here, and those things are no longer linked. They become detached.
You've broken the system basically.
Broke GitHub.
It's
broke.
Well, yeah. I mean, it's just it just makes it. What it does is it makes it messy and it makes it hard to follow what happens.
It makes it messy, and
so we want to avoid that, right?
Yeah. Well, I mean, I will tell you, I'm on teams right now. We do it not on a daily basis, but certainly on a weekly basis. And every time we do it, we have to go clean it all up because something went awry for whatever reason. But you want to avoid that.
So I'll tell you guys that I did that because I didn't know what I was doing years ago, and since I've figured out and learned these kind of basic things to stick to that work, I haven't had to worry about that for years now.
Mm-hmm.
And it's better that way because it's you can get really confused and messed up quickly.
Yeah, okay. And if you're working by yourself, it's not as painful. If you're working in a team, let's say 20 people, and you just pushed up a bunch of stuff and it overwrote half of somebody's stuff and a little bit here and a little bit there, and God knows what you changed. Now everybody else is cussing you. It's not good. It's not good.
Carl, I have a question. Whenever you do a merge, it still shows you what was, the old section of code and what changed a new section of code, right?
Yeah, I haven't shown you that. We got a little detour. So we just
that doesn't go away, right?
We just did the pull request. There's no pull request open because we did this and merged it, right? So we've just done the first merge to this repo, and if we do a refresh here, you can see it.
Yep.
So it has taken this head in GitHub and it merged it into master.
Yep.
Right. So, and that's what I like about this is that it shows that pretty clearly.
Okay. So after you do that, the merge, I've seen it where there's like a red highlighted section of text, which I think represents the old stuff, the green, which represents the new. Does that ever go away after a merge? Or does that always stay there?
So I think what you're asking is how do you, I mean, that's a view, right? So like here, in this one, we did a minor spelling error correction, right? And that was in main.txt. So we can compare main.txt to the previous, and then we can see that that's where we had these extra D's and I got rid of them.
Right. Okay. So that was just based on one commit. Say you do another commit. Does this change go away because it was associated with a previous commit?
Oh, no, not at all.
So it stays there forever.
Well, until it's changed again. So right now, so what we can do is let's get the master, because right now we have the master on GitHub ahead of the master on local. So let's get the master on local up to date. So we've checked out the master, and now you'll see that it shows that there's 2 commits to pull down from GitHub to local, and there's no commits to push up. Okay, so we'll hit that button, push and pull. And now if we refresh this tool, we can see that they're in sync. So like now if we go to main, and there it is. There it has the correct spelling because we didn't change it, which is another thing you can do with this tool. I don't know how you do it in other tools, but like I can say, well, what's changed from this commit here? So I'll select this commit, this 335 one. What's changed from there to way up here? Compare. And down here, there's the thing showed up, compare commits. Well, in main, there's the D's, they got changed. And then we had these new files added. So, and it shows you right up here in the compare window, from this commit to that commit, from left to right what changed.
Yep.
So it's pretty cool then, because you can compare across branches, across long periods of time.
Okay, so say you branched, made some changes, and then merged again. The history of all those changes, are those kept in the files?
The history is kept buried in this magic folder that you never touch by hand.
Okay.
So, and unlike other repos, which I've understood before Git, there was a number of versioning tools that they would store a copy of every file, whether it changed or not.
Mm-hmm.
And one of the smart things that I've understood Git did was, by design, it only changes files or things that it only stores things that change.
Okay.
And instead it builds a table of references down in here. So that's how, like, I can go, it detaches the head, but we could go right now, we could say, let's check out this commit. And we've now checked out that commit right here, whatever that is, 335. It's detached from the head, so it's kind of a bad form, but sometimes it can be helpful to go back like that, copy things out. But we're not going to do that. We're going to say, let's take the latest and greatest on master.
Mm-hmm. Okay.
And now we see that the feature branch, look at the timeline, right? Because we had good progress in the feature branch. Then somebody went and added a repo and the other location up on GitHub. And then through this combination, we brought them all together. So now the main branch has all the goodness from everywhere. So in a way, the main branch, the master branch, is ahead of the feature branch because it has more things in it.
So, Carl, if you're using two machines, this is one of my questions.
Yeah.
As if you had your desktop and your laptop, every time you worked on it on one of the machines, the last thing you would do is make a commit.
Yeah.
So that
and push. I'd make a commit and push it up to GitHub.
Right. So that way, when you started off on your other machine, you would do a pull.
That's right.
Basically. Okay.
Exactly. Yeah.
Gotcha.
Yep. And that, again, there's another that raises the point that, like, is actually another good segue, because, like, right now the master is ahead of everything. So like, what happens if we wanted to do some more work in the pretend feature branch? Well, let's check it out. And but we know from looking at the history that it's behind the master. So how can we quickly catch it up to the master? Well, if we did this, it's only going to synchronize with this. It's already in sync. There's nothing to pull down. But what we could do here is we could go to command line and we could do git pull origin master. And what that would do is say, let's pull all of the changes from GitHub and the master branch in GitHub, and let's pull them into the current commit, which is pretend new feature branch. All right. So what's that going to do? That's going to take these changes that are up in master and pull them down into here, right?
Okay.
At least I hope. Let's see. All right. And now if we refresh this, that's what it did. See that? So it caught up the local branch with master, but now the GitHub is behind. So now let's see, we have no changes to pull down from GitHub, and we have 2 to push up to GitHub. So we can click that button and it does the sync, and we refresh. Okay, great. Now we have all 4 branches at the same point, and we can keep working on our pretend new feature branch.
Or so it would branch off again, Carl?
Sure.
It make another little loop.
Yeah.
Oh, wait a minute. You just hit create new branch. Don't create a new branch. Don't.
Okay.
Okay, but make a change to origin pretend. Just do something.
Okay. We'll do a change. Okay.
And now
another change for this new feature branch.
Okay. Now, if you commit that,
Okay.
what is it? What is your graph going to look like?
All right. So first we got to go over here and we got to stage the change, right?
Yeah.
So we've staged it. Now if we commit it, all right. So now right away you see that it's got none to pull down, one to push up. And if we check here locally, all right. And if we push up to GitHub, right? And now we're back in the same thing, right? Because the feature branch is ahead of the master. So we can go over here, we can do another pull request, or we can forget that and we can just pull it in locally here.
Okay, so now go back to GitHub and make a small change to the README file.
Okay.
And then
on which branch?
Thank you.
On the master.
On the master, okay.
Yeah, that's where you are.
How do I edit in?
Let's see, it's an easy way to edit these. I'm not sure exactly how, but
yeah,
I haven't done it before.
Oh wait, it's
there. It is.
Pencil.
Yeah.
Okay.
Just a small change. Okay, now this should create that other thing to pop back off the master line is what I was trying to see.
So we'll commit this.
Okay.
All right. So now if we refresh, I think we have to go, we did that on master. So we'll go to master and we have one to pull down. And we'll refresh.
Okay,
Yep.
that's what I wanted to see. Okay,
Yep.
so the same branch, the same branch popped off. Okay.
Yep.
Yeah.
Yeah. Mm-hmm. So we started at that point and we started making changes on whatever that file set was. Take it as far as we want.
Okay. Boy, Carl, this has been really helpful. Thank you.
You got it. Let's see. And is there anything else?
I've learned more in the last 45 minutes on merging and branching than I have like in the last year.
Oh, Carl, you haven't brought up the other big religious debate that I believe.
What's that?
Rebase or merge. We've been using the term merge. We've been using the term merge in turn. I mean, that is a very, very specific meaning.
Yeah. Yeah, and it's important. Harold, I was trying to get to this basic level. And there's actually one more thing I was going to show, but I encourage you, Harold, that and if we think we should go there, that we should do another session.
Well, I only want to bring it up because if you talk to somebody else, you may hear that I never merge, I rebase, and it may confuse you. The operation is the same. Okay, the operation is different, but the result, the result is different, but the end result is the same. You're taking two different copies of the file and getting a single file out of it that includes all the changes in both files. In a merge, it does a line by line merge, and you can imagine, because you can see it in the text file to do that. In a rebase, it rewinds, it changes the history. So this history thing that you were just all talking about, it changes that because it rewinds both of those files so they're both the same, and then plays it forward, and whoever gets their stuff in, and that's what goes on. And so it plays those changes on top of each other in a historical kind of way. Okay?
Yeah, when I was looking at it, all the branches in the history that are popping off to the right and merging back in to the left, they're all gone. It just becomes one big series of commits.
It becomes one big series of commits, exactly. And in the merge world, that operation will have a merge conflict. Say, I changed this line, Carl changed this line, and now which one is the right one to have? And so they want a human to go in there and look at that and decide which one it's supposed to be. And usually it's one or the other. Sometimes it's a combination of what was done on each on that line. That's a merge conflict. So a rebase avoids that conflict, but it may not get it may get your changes in differently. Because in this, what would happen in that, Carl changes line, I change the line. I changed it after Carl. So if we rebase, Carl's line goes in and then mine goes in. So yeah.
So let me give you a real world, a really practical example, because the first time I heard of that, it was 12 years ago or so, and I didn't understand it all that much. But okay, so this was when I was working at TerraStar, and there's a group doing the radio modem code basically for a phone. And they had taken from a vendor this large stack, which operated the radio modem for a cellular phone. Okay. They took a snapshot of it, they forked it, and then they made all sorts of changes to add a new radio. So they took the terrestrial radio and they added whole new set of code that would adapt and allow it to also use a satellite radio. But then at some point, it took so long, and we had to get back through certification. So it meant that they had to pull in the changes from the original vendor. So they'd been making the changes to add a satellite radio. The original vendor had been advancing the code to keep up with the terrestrial network operators. So at some point, then we had to catch up so we could get the latest terrestrial code. So the question was, do we try and merge it in, or do we try and rebase the way Harold was describing? And they actually spent about 2 months comparing it, because it had to be a bunch of line-by-line comparisons across dozens of files. And they literally got to the point where they said, well, if we do it this way, there's 700 changes. If we do it this way, there's 1,200 manual changes. And they had to do that analysis before they even dug into the task, because it was so complicated.
Yeah,
Okay, now this brings up a question, Carl. All right, so on master, I have main.txt, okay?
Yep.
All right, so on my branch, I change main.txt. So it's different than what's on masters. So now when I guess pull the two branches together, what happens to the changes in main?
If you've only made the changes to main in the branch, then you can pull the changes from the branch over to main, and it's no problem. But if you've made changes in main in the branch, and you've made different changes in main in the master, then you're going to have one of these conflicts, and you have to resolve it, which I didn't want to get into today.
Yeah, but I mean, is that where you use the rebarb?
Rebase or merge. I mean, there's a lot of tools, a lot of ways, and I think it covers.
I didn't mean to. I don't want to confuse everybody. Yeah. I just wanted to say that if you're talking to anybody and they'll say, "Well, I don't merge, I rebase," you're still discussing putting two files together and coming out with a combination of the two files. They're just doing it in a very different way that has a whole bunch of connotations. None of them really negative. They're just all different.
So Harold, the scenario you're positing is where you're working in a team. Most of the people on this call are not using
Git. They're not. They're not doing that.
And so it's really rather irrelevant.
So here's
I could see where you could end up doing it by mistake or something.
By mistake, but I'll put it this way: if you get yourself in that situation, bring it to a Tuesday night, and there's going to be enough people. We'll help you figure out the shortcut way or the Git way, because there's better ways and worse ways.
Okay.
I've created conflicts. Like I say, I've edited on my laptop.
Yep.
And then on my robot, and created a conflict. And when you go to do a sync, it tells you, hey, there's an issue. It's changed in two different spots. And just go look at both the spots and say, oh, okay, well, hang on, I'll just correct this. I'll move all these changes into one and then just keep the local changes.
Yeah, that's easy.
Hey, Pat, is that because you're using a Pi on your robot?
Yeah, so I'm using a Pi on the robot.
Okay.
So I have VS Code on the robot as a local, and then with the remote, and then I have the same on my other laptop, so one through VNC or one on my laptop.
Gotcha.
And so occasionally I'll create a conflict between the two. Not very often.
It's not uncommon at all when you're using two computers and making changes on both.
Yeah, as a matter of practice, though, in my experience in my work, whenever you have two branches where you have different code on each branch, the longer you go not merging those branches, the greater the risk and the greater the effort. Nothing in this system is going to save you from a really, really complex merge where you have two branches that have been changing changing separately for a long period of time. It's going to mean lots of effort to resolve the conflicts, and it's going to mean lots of testing just to make sure you got it right.
Yep.
Yeah, so that's a concept of long-lived branches, and that's another thing that we the teams that I've been on absolutely hate. Sometimes we have to do that. I'm on it right now. We have a long-lived branch going on right now. We have good reasons for doing that, but that's one of the things you try never to do, especially when you have control of the whole world. And in our case, much to Paul's point, most of what we're doing in this group in our little I don't know, our little thing, going on here, our bubble, is we're doing our own things with our own stuff, and we want to make sure that we want to make it usable, and we don't want to wipe out changes and all those sorts of things. So that long-lived branch thing, well, you get to make that choice.
So don't let us, if you're new to this, don't let us scare you off of it. We're talking about, big complex teams.
I'm going to show there's, and then I'm going to stop. So this is the closest I think that this group has come to an issue like this, and that was the the virtual line following contest that we had a couple years ago. And this is the repo that Ron Grant started, and this is my version of it. So you can see that it's got lots and lots of commits. It's got all kinds of different branches here and there, hither and yon. And that's just on this page. We can go to the next page. It just goes on, right? And there's all kinds of this monkey business back and forth. Right. And we had in here we had his example robots and other different robots in here. So big repo. And then the only other thing that we haven't talked about yet, which I think might be useful for this team at some point, and that is that you remember that git remote command that I showed you? Well, would you look at this? Here we have this remote. It's pointed to origin, which in my case is my own GitHub repo. It's pointed to what I call origin private, which is a private version that I have. It's another copy of the repo on GitHub, right? And it's pointed to up. I've called it upstream, and it's coming from Ron Grant. So basically, Ron started this. I made a formal fork of it so that I could maintain all the references, and then I built these other two branches for whatever reason in the day. But I can keep all these straight. And in the same way that we were doing pushes and pulls just on that demo repo we did just to origin master, we can do pushes and pulls to any one of these different repos. So master is all a state of mind, right? You just have to think about, okay, I just did changes from this point of view. I want to push them to that repo in that branch, and the system will keep track of it all for you. So for whatever that's worth, there's a real world example. And this is where your mind goes, but I'm going to stop then.
In your real world example, you had a couple places where they went like that.
Yeah.
What were those?
Well, okay. So we'll go back there. Let's find, like you're talking this nonsense here.
No, go further up.
Further to.
No, it's pretty clean there. It looked like there were a couple places where there was.
It was really twisted.
Really twisted, yes.
Like here.
Yeah.
No, even more than that.
It was even more than that. There.
Oh yeah. Yeah, this was if I remember right, this was sometime when I really screwed up. So so you can tell Ron did this update to the README, and then I merged. So Ron did this README change right here, right? Which at at the time was what? A handful of things, his nlap deal. So Ron made a handful of changes. So then that we go from that commit to the next thing that happened was not even 2 hours later, I merged his change into my everything on this head. I merged into my branch, and then I apparently made a new branch from his over to, or no, I pulled the changes from here into whatever this other green branch is, and that involved pulling in all kinds of crazy changes. Look at that. And this gets into git ignore, which is something I should have mentioned and I didn't. We can do that another night. Because there's some files you don't care about, like intermediate build files from the compiler. There's a way to say, hey, Git, just ignore these.
I thought those were ignored by default.
No, they're ignored by your specification.
That's what that git ignore.
That's what dot git ignore is. And I don't know if that's in here or not, but yeah, that's what this file is. So right now, like File Explorer, dot git ignore, and right now, and you can see, look at it, isn't that cool? Ron Grant did it a year ago, September 29th, 6 in the morning. He added bin and temp. So he's telling Git to just don't even bother tracking these files. But so in this nonsense, so Ron did that. Then I merged his changes into my, must have been main branch. Then I merged those changes over and I pulled those into my probably working branch. And then Ron got ahead of me. So he did 1, 2, 3, 4, 5, 6 commits until I went and I took his commits and I merged them back into mine. He did some more. So you see how you can follow it along there, Dave?
Yeah. Thank you.
Yeah.
So basically, it's where you're taking the stuff from one branch and merging them into the other.
Yeah.
Okay.
Now, is that the proper use of merge?
I think so.
Or is it to push? You're taking stuff from one branch and pushing it into another branch.
That's called a PR.
Pull request.
A pull request is what that is. A push is always a push in this context. You're pushing something from your local branch into the repository, the central repository.
So
when you want to take your branch and get it into main or master, whatever you're calling it, or sometimes if it's a long feature branch we're just talking about, it's just another branch. That's a PR or a pull request to pull my branch into your main and master. That's just another branch. We just call them special names. Pull that branch into another branch, and that's a pull request.
Okay, got it.
Or a PR is what we usually say. We interchangeable use of those words.
And there we have it. So there's there's other services like GitHub, by the way. There's Atlassian Bitbucket, AWS Code Commit, but GitHub is really common, and we have Microsoft people in the group, so we'll use Microsoft product. But I do.
Yeah, but use whatever you want. Bitbucket, GitLab, they all use Git.
But I will say, if you search for how-to stuff, of all the documents I found, the Atlassian how-to and how these things work, they have the best explanations from what I've seen. If you're just searching the web, nice diagrams and clear wording. So that was it.
You're saying in terms of VS or in terms of just GitHub?
What was the question?
When you're saying you go search for the stuff, you're searching it in context of VS or in terms of
good question, and I'm just rambling without being clear. So let's do an example. So let's say we want to do a how do I do a Git rebase? And I'll just search down here for the last, like, these are all good references. Don't get me wrong. JetBrains, Git SCM is like the formal, but I'll just jump down to Atlassian, and they have these nice tutorials. This is the people that do Jira and Confluence, but they have these nice diagrams on what it is, right? And they show the words that we've just talked about, the main branch, and you got some feature, you got a new feature. So they talk about, what it is, how to use it. And they walk through the steps of using it with the command line way. But if you can get the concept through here, then I found this is useful. That's all I'm saying is that if you search on how to do something in Git, look for the Atlassian one, and here's merging versus rebasing. Harold.
There you go. Sweet.
This made, golden rules, right? So best practice is how to do it. What are the workflows? Conceptually, what's different? What's going on under the covers when you do these commands?
I really like how they're doing the dots and the arrows and all that kind of stuff. It makes it easy for a dumb ape brain like myself to be able to understand it.
Amen. Same here. Yep. So I spent a lot of time on these, and then I said, screw it. I found a simple ways to stay out of trouble and make it work, and go back to those anymore.
I think you'll find going forward, if you start doing this, you're going to find like, this is crazy. I don't understand it and that kind of stuff. But if you keep at it just a little bit, you'll come down to about 4 or 5 commands that you'll use all the time. That'll do everything you absolutely do. And if you get yourself in trouble, then that Atlassian thing is a good resource. And all this stuff, if you do it enough, it'll all become finger macros, and you won't even know what you just typed because you just did the right thing. So you're used to doing a thing.
And if you're Atlassian also has an app called SourceTree, which is really nice if you don't want to use visual.
SourceTree is a nice graphical thing. SourceTree is a nice graphical Git thing. It's under the covers. It's doing all the stuff you would do with the command line, but you don't have to remember all the parameters and what a cherry pick actually does, and all this kind of stuff has to happen. So it's a nice thing. I've used it before.
I think it also makes it easier to do like conflict resolution, right, Harold? I think.
I don't know about that. I use a tool called Beyond Compare, and I paid for it several years ago, and I've got a license that goes for Linux and Macs, and it's a little expensive. But if you don't want to pay for it, there's a couple tools out there. The built-in Git version of this stuff is horrendous, but if you look for something like on the Windows platform, WinMerge is there. I'm just so used to Beyond Compare, which is free. They have an interesting thing. Beyond Compare is a fantastic program, fantastic, and their licensing model is weird because they give you 30 days of use on it. And like, what's weird about that, Harold? What the weird part is, it's 30 days of use, not 30 calendar days. So I own a license. I've got the client I'm on now, which I've been on for 8-9 months or so. I used that a couple of times, and I still have 26 days of free usage on it. So literally, you fire it up on a day, you get 24 hours to use it before you lose that day on the thing. And so I've been on projects where and it's been on my projects running on a client's machine. I've just used that trial version the entire length of the project without having to put my license on it. And I was really ready to put my license on it because their licensing allow me to put it on anywhere I want, just as long as I'm the one using it, regardless what machine it's on. It's pretty liberal in that way. So you might want to go look at Beyond Compare, and that conflict, if it only happens to you once a year, you may be years before you run out of that free software version of it, the free tutorial. Just a point of reference. But there's a tool. I don't know if SourceTree is going to help you with the merging. I don't know that's going to help. It might, but I think it will.
But yeah, some of those when you have conflicts, they make it easier than others. But
and sometimes Git's pretty stupid about the conflicts. It's like I don't know what to do here. And I'm like, well, I had 2 more spaces at the end of the line, figure it out, dude. And Beyond Compare and other tools like that will handle that, where the standard Git stuff won't. The standard stuff you get, it's pretty stupid.
So give it a shot, guys. If you get stuck, share your screen and we'll help you through it.
Is that a pun? Get stuck?
Oh,
or is that just another command?
It gets. We should do a PR and add that as a new command.
I think that's actually a derogatory kind of thing going on there. Like get stuck.
You can create an alias in Git, but we won't go there either. We can call it. Okay. So next in queue, I'm sorry I took so long. Hopefully it sounds like it's worthwhile for some at least. So next in queue, we had Doug P with something. And then
I wanted to, actually what I wanted to do is like Chris, I went through Dave's presentation again to make sure what I was trying to do is figure out the differences between how he does things and how I do things. And so I really want to go is kind of go over what I think Dave is doing. So he can, while he's here, he can say, no, Doug, that's wrong. Or, yeah, that's the way I do it. So let me present and let me I'm just trying to make sure I understand it, because there are some differences, but I don't think there's a whole lot of differences. But let me go ahead and present.
And maybe in the process, you can address the conflict where I said, no, David clearly said this. And David said, no, I didn't clearly say that.
Well, I have to admit, Paul, that's what got me. Okay, now I was confused and I needed to read over it again to make sure I understood what I thought was going on. Okay, so, all right. No, that's not what it's supposed to be hidden. Okay, here it is. This is what let me go ahead and present this. See if I can find the present button. There it is. Why isn't it not do start from current slide? Okay, so Dave, this is kind of what I saw you doing. So this is just a PID rule, PID controller, motor with encoder. And from reading the things, it looks like you have a clip function here. Then you have a normalized rotation value and a normalized velocity, which come from your arbitration. So those get positive fed into one and negative fed into other. Then they go through a clip function where they're limited from -100 to 100. Then it goes through here. And I wasn't sure about this. It's -100 to 100 of whatever the power of your motor controller is. I don't know if it's an 8-bit, it might go from 0 to 250, 255. And then that drops you out a direction and speed, which is in PWM from between 0 and 100 and drives the motor. And then your feedback, the encoder counts. Does that look okay? Is that what I see you doing? I'll give you a second here.
Yes, the only tiny modification I would make is that since I'm using integers for everything, those values are actually -1,000 to 1,000. So I think of that as 0 to 100 with a 0.1% resolution. But yes, yes.
Okay. So the real trick then is where are the normalized, where's the velocity and the rotation coming from? And this I picked the rotation value for the navigation behavior because I figured that would be the most complex one. And so it looks like if the target vector if you're at the target vector, it returns a true. If the bearing is less than the dead zone and the bearing is greater than the negative, then your navigation algorithm is the slew rotation of 0. And here's where it is. So this is the value. It's the PNav rotation rate, I think. Okay. And if it doesn't come out, if it's not, doesn't fit that, then if it's greater, you go left or you go right or left. Okay. So here's how I interpreted that. So you have some dead zone where if you're in the dead zone, you just go straight. These represent possible waypoints with relation to where your robot is. So if then you have your slew limits. So if you're inside these slew limits, you're going to turn left at a reduced rate. If you're outside of that, you're going to go at the slew rate, max slew rate. Okay, does that make sense? I'm not sure.
I'm not sure either.
Okay, so
let me well, go ahead, Doug.
Okay, so here's the graph that you presented. So, and what you have an area in between where it looks like it has a linear slew rate till you hit the limiter. Okay, so what I assumed was that between the deadband limit and whatever this, if the turn is greater than what you need, then this rate, here you're going to be linear, and then out here you're going to be slewed. You're going to be at the max slew rate. So
No,
if the robot tries to turn.
That's not exactly correct. And let me think about what the right way to say it is. The slew rate limiter is limits the rate by time. All right. So to use a simple example, suppose you had a slew rate of 10 and you're trying to get to a value of 100, then it'll take you 10 times through the control loop to get there. But suppose the first 2 times through the control loop, you actually make the correction needed. So you never actually get to the max value. The smaller values bump you back toward the target and put you back inside the dead zone. So the longer you turn, the larger. I can't think of the right way to say this. Obviously, if you're going to have to go through the loop 10 times to get to the maximum rate, if you only go through the loop 2 times and the condition is met, you're going to have a much smaller value. So there's not like an edge there that you drive over and suddenly click from one behavior to another, but rather the longer you turn, the sharper you turn.
Interesting.
You don't look like that's making it any easier. Let's suppose that your target is actually in the deadband. Okay. And basically the robot is now drifting over toward one side of the deadband, but you're pretty close to being straight. You're not off by very much, but you're drifting off. Okay, so now you hit the edge of the deadband.
Where my thing is right now, my cursor.
Yes, you hit that edge of the deadband, and that's what triggers the behavior. There is no behavior while you're inside the deadband, but once you hit the edge of the deadband, it triggers a behavior for where you are, saying turn back to the right. Now, suppose the first time through the control loop, again, use the example, we're going from 0 to 100. So the first time through the control loop, you get a 10. And the second time through the control loop, you get a 20. Well, maybe that 10 and that 20 is enough to push you back inside the dead zone. And so you're no longer triggered. The behavior is no longer triggered. So just a couple of minor bumps bumped you back inside of the deadband. Now you're drifting really slowly over to the other side of the deadband, and you hit that side of the deadband. But let's say you hit it a little more sharply. So maybe it takes 3 times or 4 times through the control loop to correct. So now, again, we're shooting for a turn constant of 100, but we don't get there. We don't get there because by the time we get to 10 or 20, we've already corrected. So you stay inside the deadband. Now let's.
So is this a constant? That's what I guess that was not clear.
Both of those are constants.
This is a
rotation.
Okay, the confusion I think is that it's an additive thing. where the first time through it says, okay, add 10. The next time through it says add another 10, which gives it a 20. And the next time through it says add another 10, which gives it a 30.
So you have to go through the loop 10 times. In this case, with a slew rate of 10 and a target of 100, you'd have to go through the loop 10 times to get to the target. But the correction may have happened long before then. So you actually can get a very small correction, even though you're saying a constant rotation rate of 100. You never actually get to 100. Now, suppose that the point we're trying to get to is that one you have out there to the right. So that's way outside the dead zone. And so as you begin turning toward it, you probably will slew all the way up to 100. So the turn will get tighter and tighter until you drop inside the dead zone. That I didn't go over that as thoroughly as I probably should have in the talk, but there's profound ramifications to using those slew rate generators in the way the behaviors interact with each other. And you can't just look at the turn rate constant and the rate of change constant and know what the robot is doing, because there's time involved. You have to take into account how long it did that. The longer it did it, by the same token, I think it was when I was demonstrating the IR avoidance behavior, I said, if you see left or right detection, it slows down to half speed. Well, it depends on how long it saw that detection. If it just saw it for an instant, it just slowed down a tiny amount. By the same token, if the forward-looking IR sees something, it slows down to 0. So what that means is that, again, if the forward-looking IR just saw something for an instant, it doesn't change very much. But as you approach the object, you'll actually stop moving forward at all and only be able to rotate. And the amount of time it takes to do that deceleration is controlled by the rate, by the slew rate. Is that any better, Doug?
Well, I'm still having a little issue. Okay, would you agree with David's statement that every time it's a constant, say 10, and then it increases every time you go by 10 through the loop? And is that what you're saying? Is that true? That's what David said. David Ackley commented that this is what was going on.
David Anderson, you're muted.
How about now?
No, okay. I can hear you. So
yes, David Ackley's comment is correct.
Okay, so this is what's going on.
If you back up to the algorithm there, can you do that?
Yeah.
Okay, if you look at each one of those, there's a slew rotation. That slew rotation takes 2 arguments. So look at the first one. The first argument is the target. So we want a rotation of 0. And the second argument is the rate at which we're going to get to that.
So
those are both constants.
Yeah, but what is this now? You say 0.
Oh, you can't see my mouse. I'm sorry.
Yeah.
Okay, so we want to go straight. If you're inside the dead zone, go straight.
Right. That's up
So
here.
that means no turning. That means our rotation value needs to be 0.
Yeah, I see it right here.
Okay, so navigate.arg is the rotation value. But we may not be at 0 initially, and we don't want to just slam to 0. We want to slew to 0. So at whatever rate P nav rotation rate is set, which will be a constant on the order of 10 or 20 or something like that.
So it's really nav turn that changes every time through the loop. The rate is a constant.
The rate is a constant. The rate is
so this is the
and turn.
This is the value.
Okay, now both of those are constants. Anything that starts with a P underbar in my code is a constant that's set by the user.
So it's not pointer. It's not pointer.
No.
Okay.
It's a parameter. P stands for parameter. So both of those are constants. And as I say, you can't trust that means that the turn is a constant, because that depends on the slew rate and how long it turns.
Okay.
So PNav turn is just a constant. It says, what is the constant curvature that you want to use when you're navigating? And it can be less than that, but it can also be more than that, because we're also slewing the velocity. And so for a fixed rotation, if the velocity slows down, the curvature tightens up.
When it has two terms in the slew, what does that mean?
The first term is what you're slewing toward, and the second term is the slew rate.
So what's the, on this one, Dave, what would be the units of nav term? Would they be radians?
No, these are velocities. So it's, plus and minus 100. Let's see, I have the code right here. I can tell you what those actual values are if you're interested.
Okay, well, so I just.
So what you're saying is that the one value is sort of the limit value, and the other one is the amount that gets added in each time?
Yes.
Okay.
And those slew in either direction. So if the robot is running faster than that, it slews it down. If it's running slower than that, it slews it up.
So this is the rate, the true rate, and P nav turn is the target, basically.
Yes.
And by rate, you mean the rate at which the target is approached.
I get confused by that because target sounds like a waypoint and approach sounds like
I'm trying to get this.
And call it goal.
Would this make sense?
Okay.
For the goal?
Call it goal. That'll help.
Yeah, take the word rate out. That's confusing. PNAV term is the goal velocity.
Okay. So that would be the one, like if I said I wanted to run 50% and that happens to be 5 inches per second, that would be my goal velocity, right?
Yeah. I was explaining to Dave earlier this week that I have found it easier to specify robot velocities and rates of rotation in terms of percentage of 100% speed for that robot, rather than in real world values like inches per second or so forth, which change.
Wait, let me get that. So that's percent. What did you say?
All the velocities, both rotation and forward velocity, are scaled between 0 and 100%, where 100% is as fast as this robot can go. And since that changes from robot to robot, I found it easier to write the control algorithms in terms of percentage of full speed rather than real world values like centimeters per second or degrees per second.
Yeah, it makes this code portable too.
It percent of PWM being 100%, right?
Right. So velocities, rotation, the input to the PWM controller and so forth are all specified as plus and minus.
If I'm understanding what you said, David, I think what Doug just wrote is incorrect, because as I understand PNAV term, it's actually the maximum delta that's applied to the requested linear velocity for each motor. So it's a delta to the velocity requested by the speed control.
That's a more accurate way to say it. If you think about
again, Paul.
If you think about this in terms of just velocity, just forward velocity, let's ignore rotation for the moment. So we want to have a goal of 50%. I want to run 50% full speed, and I want a rotation rate, a velocity rate of 10. So that means it'll take 5 times through the control loop to reach that. So we'll have a linear ramp from 0 to 50. Think of that as acceleration ramp. And if you use that same thing, but you input it into the rotation command, then as Paul says, it's added to one wheel and subtracted from the other.
So if you go to the slide above where you're at the moment, Doug,
one is added and one is subtracted.
But the point is that it's I think what David is saying, if I understand him correctly, is that this angular component, the PNAV rate, might be perhaps 10, 20, 30. It's less than 100. So your velocity might be 50, it might be 80, but you would add and subtract from each wheel an amount which would peak at PNAV rate. So PNAV rate is the maximum delta.
No, it would peak at PNAV turn.
I'm sorry, PNAV turn is the maximum delta that would be applied to those two wheels, and that might be something like 20 or 30, depending on whatever its constant is.
Well, let's just maybe, I don't want to belabor this, but we're driving along at 50% full speed, and then you say, well, I'm going to turn right, and I want a right turn constant of 20, and I want a right rotation rate, slew rate of 5. So the first time around the loop, one wheel is 50 and the other wheel is 50. The next time around, one's 55 and the other's 45. And the next time around, one's 60 and one's 40, and so forth until one is 70, 50 plus 20, and one is 30, 50 minus 20. And we took 5 samples to get there, to slew there. One of the things that I've been told by other people who do subsumption, when they watch my robots run around, they always say, why doesn't it, click hard from one behavior to the other? Because that's what they think of as subsumption. And it's hard to describe to them, but by using these slew rates, it allows behaviors to fade from one to another rather than abruptly change from one to another.
Yeah. So it really isn't proportional, but it does have a time varying contribution.
Yes.
But the maximum delta is a constant.
Yes. And really what that boils down to is that when it's navigating at whatever, speed, there's a fixed arc that it would preferentially drive. But that arc can get tighter if it's slowing down, and it can get looser during the course of a slew.
Okay, I'm a little confused with this particular. You're saying the max turn is the max delta goal velocity. It's not really the max goal velocity. It is just the delta velocity, isn't it?
Well, I mean, that's kind of picky. The way we actually...
Well, no, I mean, because it increases every time through the loop, right?
But the way we actually implement is we add rotation to one wheel and we subtract it from the other. The reason for doing that is that way the velocity in the center of the robot remains constant as you steer around the room. But of course, if you're going full speed, you couldn't do that. You could only slow down one wheel. I believe Ray told me when they did the donkey competition, he steered just by slowing down the inside wheel. There are a lot of different ways to steer. But the way we're doing it is by saying, well, I'm going to add the same value to one wheel that I subtract from the other. So your diagram is correct, Doug.
All right, so I'm just
What's not correct is where he's written that PNAV term is scaled between 0 and 100, where 100 is max speed. It's scaled between 0 and 20, I think you said.
Well, it depends on max speed. It depends on what the turn constant is set to, right? I very rarely drive at max speed. Most of my robots drive around at about 50% full speed.
Yeah. So what do you typically run your PNAV turn at?
Well, I don't know. Let me go look. Hang on just a second. says here that the turn rate, now remember these are scaled to 1,000. The turn rate is 600, which would be 60, and the slew rate is 8.
So I think where Doug is written in parentheses, scaled between 0 and 100, where 100 is max speed, it would be more accurate to say slewed between 0 and 60, where 100 is max speed.
Yes. Or 60 is arbitrary.
Yeah, it's a parameter.
Yeah.
So
that you can change. This is very interesting, David. I'm glad you explained this in more detail because I didn't catch the effects of the slewing time causing a variation in turn rate when you talked about it a few weeks back. That's really interesting.
yeah, that's same here. Now, like I say, I wasn't sure if I had this really understood, and that's why I wanted to make sure I tried to capture exactly what was going on.
Well, I hope I'm doing better this time.
Well, I want to make, so you said this was 0 to 1,000, and it's an integer, right?
Yeah, I just do that because I wanted to have more resolution. And, with this new STM, this ARM chip, I could do it all in floating point, but, the US missiles are all guided in fixed point.
Mm-hmm. Yeah, and this would be minus 100 to 100% power because I don't know what your motor controller asks for.
Exactly.
But it's got to be something.
Well, and what I do, Doug, is I go back and I measure that. So I can tell you, because I was just looking at it, that for the RCAT robot, the 2 motors on it at full speed, that is at 100% PWM, at 100% duty cycle, those motors run about 5,322 counts per 40 milliseconds, which is my 25 hertz loop rate.
Okay.
So what I do is I take 5,322 and I divide that by 1,000, and I call that the velocity scalar. And that way I can scale the velocity, the encoder counts, into the same range as everything else. So
you're saying, so you don't actually feed back encoder counts, you field back the scaled encoder
yes.
counts.
And one of the reasons I can get away with that is because I've got so many counts that I can divide them by 1,000 and still have lots left over when I'm driving real slow.
Okay, so
I think if I had fewer encoder counts, I would instead I would modify, or I would recalculate the requested velocity to match the encoder counts. Basically, here I'm recalculating the encoder counts to match the requested velocity range.
So, and that's basically, come on, Doug. So that's, Jesus, max speed divided by 100.
Yes.
No, max encoder counts.
The max encoder counts per control loop iteration. As I say, I have a surplus of encoder counts on this robot, so I could get away with things like that. On robots.
And as long as you're fixing up this diagram, since you change the flip function to minus 1,000 to plus 1,000, you should change the normalized input velocity to minus 1,000 to plus 1,000, and the angular component to be a parameter, nominally minus 600 to plus 600.
No, just 600.
Yes.
600 in a range from 0 to 1,000.
Yes.
Doug, in my own notes, to make that clear to myself that I'm using fixed point, I usually write that as 100.0%. That way I remember it's really an integer between 0 and 1,000.
Okay, so you guys, am I getting closer? This should go over here, and there should be another little block.
And of course, it's actually max encoder counts divided by 1,000, but if you want to put divided by 100.0, that's the way I do it.
Okay, where was that? Where was that, Dave? I missed something.
Top center.
Top center. This up here?
Scaled encoder counts is max encoder counts divided by 1,000, or as I say, 100.0 is how I write that.
Out by per 1,000 per loop.
Per loop, yeah.
Yeah. Okay. Now, are these really 1 to 100, or are these one? Or they're actually 1,000 to 1,000?
They're minus 1,000 to plus 1,000.
Okay.
And think of that as being fixed point, you know,
Yeah.
1 point to the right. In terms of the pulse width modulation controller, basically on all the robots it's handled differently. As Doug said, it might be, you know, 8 bits control on one and so forth, but basically minus 100 is full speed backwards and 0 is stopped and plus 100 is full speed forward.
Yeah.
If you think about that in rotation, you understand why there's that clip function in there. Because if I said I want to go 100% velocity with 100% rotation, you end up with, you know, 200% velocity on one side, and it doesn't make any sense.
Yeah.
So that requires a certain amount of self-discipline on the point of view of the user.
Okay. All right. Let's see. I wanted. Okay.
So this one is not right.
Okay. This one's just completely off, huh?
The arrow that points there and says slew limits, that doesn't mean anything. Slew limits are time, not space.
Yeah. So this one.
And really,
well, no, this is actually still, there's some region where you have reduced rate. You have a reduced, you're not at maximum turn.
But that's
turn
true
rate.
inside the dead zone as well as outside the dead zone. There's not a different algorithm for whether you're in or outside the dead zone.
Well, you have it set to 0 though.
Once again, it is the slew rate that determines that, and that's a time function. So if the robot is in the dead zone drifting toward one side and bumps into that side, that triggers this behavior, but we don't immediately go to 100% rotation.
No.
In fact, we start slewing in that direction, and it may well be that just a couple of counts is enough to kick you back inside the dead zone. And so it never does get to full rotation.
Mm-hmm.
Same thing when you get the outside the dead zone. How long it takes you to get to full rotation depends on what that
But if you stayed in the dead zone, this would always be 0. It doesn't, otherwise, it doesn't increment, right? Or does this slew rotation function cause it? I didn't think that did. I'll have to look at that.
We probably ought to go back and look at the original code. There's another parameter in there that's assumed. I shouldn't say parameter, another value, and that is the actual current rate of the robot itself. So you're moving from the current rate of the robot to this new rate. Let me see.
Can't remember where it is.
Did that make sense? It didn't make sense when I said it.
No. So, okay, let's see if we can find that function. Well, I'll tell you what, I don't want to take everybody else's time.
Doug,
on
go back here to the earlier in the, when I was covering the slew rates was early in the talk. So it'll be one of the first slides, way back before any of this.
I'm getting here. Let's see where.
Keep going, keep going, keep going, keep going, keep going. Somewhere along in here. Go back the other way. Keep going. Keep going. Stop. Keep going. Here we go. Okay, back up. No, I don't remember. I think it's I thought it was in here.
Oh, wait a minute.
I
So
did a whole section on slew limiting.
Okay, give me a second here. I can get that function.
There you go. There you go.
And we should be able to
search.
Go up here and do. Okay, that's not it. Nope.
Yeah, here we go. Okay. Now look at the function there, the second function called float slew. Slew has a from, a to, and a rate. All right. Okay. So slew rotation only has a to and a rate. It has no from. All right. So scroll down here a little bit and stop right there. No, keep right there. You'll see that the motor command, which is handed a velocity and a rotation, saves those two. One's called bot velocity and one's called bot rotate. That's the current velocity and rotate commands that are sent to the robot. That's where the from values of that slew come from. So scroll on down one more page. And you see there, slew velocity uses bot velocity as the from value, and slew rotate uses bot rotate as the from value. So that thing we're looking at that said slew rotate 0 at a certain rate, that means to slew toward 0 from whatever bot rotate is now. And we don't know what it is now when we call it.
Okay, it's going to take me a little bit more to look at it. I don't want to take everybody's time, but thank you.
I hope I hadn't made it worse.
I don't think you made it worse.
I think the confusion factor is that this is not a continuous function. It is a discrete function. That is, it goes tick, tick, tick.
Yeah.
Hey, and then the audio freezes. Oh no.
I think you're trying to think of it as a continuous function, whereas it is a discrete function. It gets run now, gets run again, gets run again. So it's incrementing through. It's not becoming instantaneous value. It says, add this amount this time. Next time, add this amount. Next time, add this amount.
Yeah, here it is right here. This is what I was missing. Okay. All right. I think I'm closer to what I understand what Dave's doing now. All right.
I think it is a little mysterious, and I've never come up with a good way to describe how these slew functions interact with each other, but it's a real key part of how my robots behave.
So just to make sure I understand, bot velocity and bot rotate are the current values of those at this time through the loop.
Yes. It's not necessarily the actual value of the wheels. It's the current control that was sent to the wheels.
Yeah, because this is way before the PID. This is coming from the arbitration.
Well, it's a higher level than the PID.
Yeah. So what I'm saying, it isn't the actual velocity at this point.
Yes, exactly. And by that same token, the system that Ted was describing earlier today, where the PID controller itself expects the acceleration and deceleration ramps, is a more complex PID controller. My PID controllers are much simpler than that, and the slews, the acceleration and deceleration ramps, are handled at a high level, and that's exactly what you're looking at here. This is where the acceleration and deceleration, well, this is where the acceleration ramps come from. Deceleration is different.
It would be the same thing, though, wouldn't it? Basically, you just
Well,
doing the other.
the deceleration, I measure the distance to the target, and
Oh, yeah, okay, yeah. No, yeah. I
so
think you
it's not a
mentioned that.
linear. It's not a linear ramp. The deceleration's got a curve to it, but the acceleration ramps are linear.
So where does spot? Can you go back, Doug? Where does spot velocity come from?
Can you scroll back up a couple of frames there? Yeah, stop right there. The output of the arbitrator, the output of each behavior is a velocity and a rotation. Okay. And the arbitrator passes that velocity and rotation along to the motor command. And the motor command stores it in these two values, bot velocity and bot rotate, which are then available to other, they're used for other things, but they're used by the slew controller. Oh. So as a matter of fact, if you go forward 2 frames, Doug.
This one?
Yeah, stop right there. If you can picture the 25 hertz control loop. So we started at the top there and we fell down through, and let's say all the other behaviors are disabled. So only this default behavior is enabled. And it gets its user velocity and rotation from a knob, or from a constant that's set by a knob. Let's suppose that, let's ignore rotation for the moment and just look at velocity. And say we're currently going 0 and we want to go 50%, and we have a velocity slew rate of 10. So the first time through that loop, that command velocity will be 0. So the arbitrator will pass a 0 velocity and a 0 rotation onto the motor command. And the motor command will calculate the left and right motors, but will save the original bot velocity and bot rotate. So now we go through.
Okay, so now, okay.
Okay, so now we go back up to the top of the loop again. And this time when we come through, the robot velocity is now 10. It's not 0 anymore because we sent it a command of 10 last time. So this time through, we'll add another 10 to that and it'll be 20. And so the velocity the arbitrator hands to the motor command will be 20, and the value that's saved in bot velocity will be 20. So the next time around the loop, and so forth. So as I mentioned before, the slew command has a from, to, and rate. And slew velocity, the from is this velocity here, bot velocity. And for rotation, the rotation rate is bot rotate. And then
so
those.
Are you saying that the slew command takes effect up above the motor command, up above those velocity and rotation inputs to the motor command?
It's in here in the arbitrator.
It's in the arbiter?
No.
Well, no, excuse me. It's in the default.
It's in each individual behavior. Each behavior has its own constants and slew rates. And so each behavior is responsible for its own slew rate. So in this case, if you scroll down maybe, or maybe up, I think down, I actually put in the default behavior. No, go back up maybe. Yeah. No, it's this one here, Doug, the one you just scroll past. So I said there's a little command block that has a command and an argument and a flag. And the command is the velocity, the argument is the rotation, and the flag is the subsumption flag. So the command here is to slew the velocity toward a velocity set by P user velocity. That's me, that's the knob, at the velocity rate, which I think is 25. And same thing for the rotation rate. So that's all the default command does. It just passes those, but it doesn't pass them straight through. It passes them through this slew command. So when this behavior takes over,
That's this up here.
Yes.
Default command and argument.
Yes. So when that default, and you can scroll back down to our control loop here, assuming that nobody of higher priority is running, the default behavior will run, and the default behavior will then take off whatever one of those previous behaviors, if it was running, wherever it left rotate and velocity is where we'll pick up from. That's where default behavior will pick up from, and it will slew whatever current velocity is to the required and whatever current rotation is to the required.
So really, this here really should have been P user velocity.
Only
times loops.
Only if the default behavior is running.
Yeah, but I meant, well, that's the example you've got here. You're showing this to be the one that passes. Now I can't remember where. I know you've shown the. Oh, where is it? Somewhere you show the 3 commands that get passed here.
Yeah, I think there's just a typed F if you scroll up a little bit. There you go. No, keep going up. Nope. There we go. So each one of the behaviors, that's what its output. Its output is written to a command block, and the command block has a velocity of rotation and the execution flag. And that's what's
the bot velocity and bot rotate values actually come into play when you do a transition between behaviors, because the new behavior that gains control starts off slewing from the current the value of bot velocity and bot rotate that was left by the previous behavior.
Exactly.
Wow.
And it did on a per behavior basis too.
Yeah. That's way more.
So for example,
I did not realize that at all. I thought it was like all down in the motor control.
That's deep.
So for example, the sonar and the IR turn the robot much more quickly. They have higher rotation rates and they have higher slew rates than, say, the navigation behavior, which tends to drive more slew. Yeah. Also, for the sonar and the IR, anytime they're active, the robot's going to be slowing down. They always slow the robot down to about half speed, or half whatever the current speed is. So that, as I mentioned, tightens up the turns.
Okay, now Dave.
Do they slow it down immediately, or do they start slewing it down?
Well, Dave, if you look, when you go to 0, you do it at a slew rate. So yes, they slew it down to 0.
Okay, thank you.
The only place I don't use the slew controller is in the bumper behavior, where if it slams into something, we don't need a nice pretty slew. We got to get out of there.
All right, now Dave, let's go to this. Okay, this was one thing I couldn't quite understand was, okay, turn sharply towards. That made sense, I think. But why is it turn gently away? I mean, let's see. Oh, this is a wall following.
Yeah.
Okay. All right. Okay. Gotcha. So this is the distance that you want it to be from the wall.
Exactly.
Gotcha.
And then you want those corrections. If it's just a little too close or a little too far, you want those to be very gentle corrections, so it doesn't end up swimming along the wall.
Mm-hmm.
But if it's way too far, it probably means that you turned a corner, and you need to turn real sharply to make that corner.
Gotcha. Okay.
Doug, I think we're driving everybody off.
I'm sorry.
No, I'm really glad you asked this, David and Doug, and I'm really glad you explained it in more detail, David, because I now understand it a lot better than I did previously.
Well, Carl, if you've still got 5 minutes, I can show what I got here.
Okay, I'm so.
Can you
Yeah.
save it for next time?
Whichever y'all want to do.
No.
I'm sorry we let these go as long as
That
they
was a
did, but-
long 10 minutes.
Yeah, so was my 40, but we
I
still
wanna
had
hear-
you all in, John, in queue. So
Yeah.
I mean, if you guys want to continue, we're here. And if you want to
Yeah.
do it next week, that's fine.
Next week.
John, you going
Next
for a
week.
star?
Good
Paul,
idea.
Paul's
Yeah,
already got a
if
star.
you got 5 minutes, I'll show you what I got. And it's
Okay.
really 5 minutes.
Okay.
Real
Let's
do 5 minutes, and then
Let's do
after
it. And then
that,
we'll
All right.
catch Paul up next week. We'll give you a proper time, Paul.
yeah, because it's 11. So
So can you see that? Those two video screens there?
Oh, Oak Delight, huh?
All right. So on the left screen, that's the face detection software running on the Raspberry Pi.
The Raspberry.
And then you can see the eyes over here on this screen. And if you can look, you have to look close because I've kind of got a kludge set up here. You can see the eyes following my face.
Yes.
Can you make the
Yes. Cool.
can you make the window for the Pi camera stream a little larger?
No, I can't. It's fixed.
Okay, I see it now.
Oops.
Yeah.
If I move suddenly, you can see it.
Okay. Yeah, I see it now. I think that's a star.
It's kind of jerky.
Absolutely.
It's kind of jerky, so I'll have to find ways to improve the performance or smooth the performance of the eyes.
Wow.
That's it.
That's pretty awesome. Look at that. We started with gold stars and we wound up with gold stars. How can we object to
Someday
that?
we may have an all gold star meeting.
Oh.
Well, I tell you what, you guys are pushing it. I mean, that was really good.
I'm feeling really bad seeing all the progress. You know, Paul and Chris and everybody are actually getting things done.
Yeah.
Dave Ackley and I have been sending graphs back and forth.
Yeah. We've been chit-chatting, and that's about it.
Yeah. But I tell you what, I think that this has been a lot of good progress this week. I mean, just incredible. Yeah. Yeah.
Focused.
I'm gonna have to get going too if I'm gonna get my rover going. So I guess this is it.
See you guys.
All right,
Good
guys.
Bye bye.
See you next
See you
week.
next week. Take care.
Always swim with a buddy.
Don't run with scissors.
Okay. Carl, you got the recording?
I just, yep. I've captured the chat and I'll stop the recording.